Hello and welcome to Sleepy Science. Tonight, we are traveling to the one place beside Earth that humanity could not see for almost all of history, the far side of the moon. It is not permanently dark. It is something far stranger, a rougher, older, and more heavily scarred world, with giant hidden basins, rare volcanic plains, mysterious magnetic swirls, and rocks that may still preserve the secret of how the moon was born. From most of this hemisphere, Earth never appears in the sky. Spacecraft lose direct contact with home, and the silence may be deep enough to hear signals from before the first stars existed. Across 90 calming and thought-provoking questions, we will uncover why the moon has two completely different faces and what its hidden side has been preserving for billions of years. Before we begin, tell me where you are listening from, and don't forget to like and subscribe. Now, let Earth fall below the horizon and follow me into the side of the moon humanity was never meant to see. The dark side of the moon is not actually dark. So why do we call it that? The moon has been hiding a linguistic trick in plain sight. The hemisphere we call the dark side is illuminated by the sun just as regularly as the face you see from Earth. When the familiar side appears as a thin crescent in your sky, sunlight is falling across much of the hemisphere turned away from you. During a new moon, the near side is largely dark, while the far side is almost fully illuminated. Over roughly one lunar day, which lasts about 29.5 Earth days, sunrise and sunset slowly travel across the entire moon. A point on the hidden hemisphere can experience nearly 2 weeks of daylight, followed by nearly 2 weeks of night, so there is no permanently dark half. The confusion comes from an older meaning of the word dark. It did not always mean a place without light. It could also describe something unknown, concealed, or difficult to understand. For nearly all of human history, that hemisphere was beyond observation, so it became dark in the sense that an unexplored ocean or an unread page might be dark. Astronomers generally prefer the term far side because it describes the geography without creating the false image of an eternally shadowed world. There are genuinely dark places on the moon, especially inside deep craters near the poles where sunlight may never reach the floor. But these permanent shadows exist on both hemispheres and cover only limited areas. The far side itself has brilliant highlands, sunlit crater walls, and long lunar mornings just like the near side. Yet the mistaken name has survived because it feels emotionally accurate. The hidden hemisphere remained invisible, silent, and unreachable, allowing mystery to take the place of evidence. This reveals something subtle about the way you understand nature. Unfamiliarity can feel like darkness, even when light is physically present. The moon was never keeping half of itself away from the sun. It was only keeping that half away from human eyes. And for centuries, not being able to see it was enough for us to imagine that no light existed there at all. Why the moon has kept the same hemisphere hidden for billions of years. Every time the moon circles Earth, it performs a perfectly timed turn that prevents you from watching its opposite face rotate into view. This is not because the moon has stopped spinning. It rotates once on its axis during the same amount of time it takes to complete one orbit around Earth, a condition called synchronous rotation or tidal locking. You can picture it by walking in a circle around a chair while keeping your face pointed toward the chair at every step. Although the chair always sees your front, you must rotate your body once during the journey. The moon does the same thing on a far larger scale. It likely did not begin this way. Soon after its formation, the young moon probably rotated much faster, while Earth's gravity pulled unevenly on its near and far sides. That difference in gravitational force produced slight distortions within the moon, creating tidal bulges. Because the moon was rotating rapidly, those bulges did not remain perfectly aligned with Earth. Gravity tugged on the misplaced bulges, gradually resisting the moon's spin. Internal friction converted some of that rotational energy into heat, and over a very long period, the rotation slowed until one turn matched one orbit. At that point, the system reached a stable arrangement in which the same general hemisphere continually faced Earth. Tidal locking is not unique to our moon. Many large moons in the solar system keep one side facing their planets because the same gravitational process has shaped them. Even now, the alignment is not absolutely motionless. The moon's orbit is slightly stretched rather than perfectly circular, and its axis is tilted, producing gentle, apparent rocking motions known as libration. These motions allow observers on Earth to glimpse narrow regions around the edges. So over time, you can see about 59% of the lunar surface, rather than exactly half. The remaining territory stayed outside direct human sight until spacecraft reached it. What appears from Earth to be a frozen face is therefore the result of motion, balanced with motion. Rotation synchronized with revolution, one cosmic rhythm fitted inside another. The hidden hemisphere has not been deliberately turned away, nor is the moon fixed in space. It is spinning with such precise timing that its movement creates the illusion of stillness, reminding you that nature can conceal enormous motion behind a surface that seems perfectly calm. No human had ever seen the far side of the moon until 1959. For thousands of years, every astronomer, navigator, ruler, and ordinary person who looked upward was limited to nearly the same lunar landscape, and no telescope on Earth could reveal what lay beyond its curved horizon. Increasing magnification could sharpen visible craters and mountains, but it could not bend sight around the body of the moon. The hidden hemisphere therefore remained one of the nearest completely unseen regions in the natural world until the Soviet spacecraft Luna 3 changed that in October 1959. The probe was not designed to land. Instead, it traveled past the moon and entered a path that carried it behind the hemisphere invisible from Earth. There, an onboard camera photographed the unfamiliar surface. The engineering required was remarkable for the period. Luna 3 used photographic film, developed the images automatically inside the spacecraft, and then scanned the processed film so the pictures could be transmitted by radio when communication with Earth became possible again. The resulting images were faint, grainy, and uneven, nothing like the sharp orbital maps available today. Yet they revealed enough to overturn expectations. Scientists saw a heavily cratered landscape, with far fewer of the broad, dark lava plains that dominate the familiar face. The first photographs did not provide a complete explanation, but they proved that the moon's two hemispheres were dramatically different. Some newly identified features were later given names, and improved missions gradually corrected the uncertain outlines in Luna 3's primitive map. The achievement was more than a technological milestone. Until that transmission arrived, no human being had possessed direct visual information about the majority of that hidden terrain. The mountains and basins had existed for billions of years, receiving sunlight and being struck by impacts, yet they had never entered human memory. Then, a small machine crossed the boundary that vision could not, captured light reflected from an unseen world, and converted it into radio signals that traveled home. The first image was imperfect, but its imperfection made the moment even more powerful. Humanity did not meet the far side through a clear window. It encountered it through blurred patches of light and shadow, slowly assembled into evidence. In 1959, the moon did not physically reveal a new face. Rather, human perception finally expanded far enough to include a face that had always been there. The first image of the moon's hidden side looked like an alien world. Nothing in humanity's long familiarity with the moon prepared us for the strange landscape that appeared in its first far-side photographs. The images were blurred, streaked, and filled with heavy contrast. Yet beneath their imperfections, scientists could make out a world that seemed almost unrelated to the smooth-faced moon known from Earth. Instead of the familiar pattern of broad dark regions surrounded by lighter ground, the hidden hemisphere appeared pale, rugged, and crowded with overlapping craters. Its surface looked less like the calm disk that had guided calendars and travelers for centuries and more like an ancient battlefield preserved after an unimaginable bombardment. Part of the alien feeling came from the quality of the photographs themselves. Shadows merged into dark stains. Bright highlands dissolved into patches of white, and uncertain boundaries made enormous structures difficult to recognize. Early interpreters had to compare several weak images, identify repeated landmarks, and slowly separate real geology from photographic distortion. Yet the most important discovery survived the poor resolution. The far side was not simply a reversed version of the hemisphere facing Earth. Its large-scale pattern was genuinely different. Only a few isolated dark areas interrupted the brighter terrain, while impact scars appeared almost everywhere. This forced scientists to reconsider the idea that both halves of the moon must have evolved in the same way. The first picture was therefore unsettling, not because it showed anything supernatural, but because it revealed how confidently people had imagined a place they had never seen. For generations, the unseen half had been mentally completed using the visible half as a model. One grainy photograph was enough to break that assumption. The moon had been close enough to dominate the night sky, yet distant enough to hide an entire geological world, reminding you that familiarity with one surface does not mean understanding the whole object. Why the far side looks almost nothing like the moon we see from Earth. At first glance, the moon's two hemispheres seem as though they belong to different worlds that were somehow joined together. The side facing Earth contains broad, relatively smooth regions that create the shapes people have imagined as faces, animals and human figures, while the far side is dominated by elevated highlands, steep crater rims, broken terrain, and densely packed impact structures. This difference is not an illusion caused by distance, camera angles, or unusual lighting. Measurements from orbit show that the far side is generally higher and rougher, with vast areas of ancient crust exposed at the surface. Its landscape has been repeatedly excavated by incoming asteroids, leaving craters inside older craters and making it difficult to find large stretches of level ground. Some impacts created enormous basins, but many of those basins were later damaged, covered with debris, or reshaped by additional collisions. The near side followed a noticeably different geological path. Large sections were resurfaced, erasing many earlier features and producing wider, flatter areas. The far side experienced far less of that renewal. So much of its appearance still reflects the moon's older and more violent history. This gives the hidden hemisphere a visual complexity that the familiar side often lacks. You can think of the near side as a page on which parts of the original writing were covered by newer ink, while the far side retains more of the scratched and damaged first draft. Yet this contrast also creates a deeper scientific puzzle. Both hemispheres belong to the same body, formed from the same early material, and exposed to the same surrounding solar system. Why then did one become comparatively smooth while the other remained so rugged? The answer cannot be found in appearance alone. It lies beneath the surface, in differences of structure, heat, chemistry, and early development that scientists are still working to reconstruct. The moon's mismatched faces quietly demonstrate that even a small world can carry two histories at once. The dark plains, covering the near side, are almost missing from the far side. The familiar dark markings on the moon are not shadows, oceans, or stains, but enormous plains of hardened volcanic rock, and their near absence from the far side is one of lunar science's most important clues. These regions are called maria, the Latin word for seas, because early observers mistook their smooth darkness for water. In reality, they formed when large impacts opened deep basins, and later volcanic eruptions filled some of those depressions with fluid basalt. As the lava spread, cooled and hardened, it buried older craters beneath wide surfaces that reflect less sunlight than the brighter highlands around them. On the hemisphere visible from Earth, these plains cover a substantial portion of the landscape and create the dark pattern recognizable to the naked eye. Across the far side, however, they occupy only a tiny fraction of the surface. The difference cannot be explained by a lack of impacts, because the hidden hemisphere contains many enormous basins where lava might have collected. Instead, the interior beneath that side appears to have released much less magma onto the surface. In most locations, molten rock either never rose far enough or failed to break through the overlying crust. Only a handful of far-side basins developed prominent volcanic floors, appearing as isolated dark islands surrounded by brighter, older terrain. This tells scientists that lunar volcanism was strongly uneven. The moon did not cool, fracture, and release internal heat in the same way everywhere. Something made the near side far more favorable to long-lasting eruptions, while much of the far side remained sealed above its deeper molten material. The missing planes therefore represent more than an absence of color. They reveal where the moon's interior once found pathways to the surface, and where those pathways remained closed. When you look at the dark shapes from Earth, you are seeing frozen evidence of ancient lava. When you imagine the far side's brighter landscape, you are seeing the places where that volcanic transformation mostly never occurred. The moon's hidden side has a mysteriously thicker crust. Beneath the far side's battered surface lies a hidden imbalance that no ordinary photograph can reveal. Its crust is considerably thicker than the crust beneath the hemisphere facing Earth. Scientists mapped this difference with NASA's Grail mission, which sent 2 spacecraft around the moon in the same orbit. As they passed over regions with slightly stronger or weaker gravity, the distance between them changed by tiny amounts. Those shifts allowed researchers to trace variations in mass and build a detailed picture of the moon's interior without drilling into it. The resulting maps showed that the lunar crust has no uniform shell. Its global average is thought to be roughly 34 to 43 kilometers thick, yet some far-side regions may reach close to 80 kilometers, while large areas elsewhere are much thinner. To understand how such an uneven shell could form, you must return to a time when the young moon was covered by a deep ocean of molten rock. As that ocean cooled, lighter minerals gradually floated upward and gathered into the first crust, almost like ice forming across the surface of a dark liquid world. For reasons that remain under investigation, more of this buoyant crustal material accumulated on the hemisphere turned away from Earth. What you see today is therefore only the upper surface of an ancient internal asymmetry. The far side is not simply rougher because of what struck it from above. Its foundation was built differently from below. That thicker shell influenced how the hemisphere responded to later heating, cracking, and geological change, quietly guiding its evolution for billions of years. You could stand on the hidden surface and never sense the extra rock beneath your feet, yet it would be shaping the landscape in every direction. The mystery is not merely why the far side looks different, but why the newborn moon allowed one hemisphere to grow a deeper protective skin, as though its earliest interior had already divided the world into 2 unequal halves. Scientists still debate why the moon developed 2 completely different faces. World as small as the moon should not have been able to hide such a large disagreement within itself. Yet scientists still cannot point to one accepted event that created its hemispheric divide. Several explanations begin during the moon's molten youth. One proposes that the early Earth, still intensely hot after the collision associated with the moon's formation, poured radiant heat onto the hemisphere facing it. That additional warmth may have slowed the cooling of the near side, while the more distant hemisphere cooled faster, allowing crust-forming minerals to collect unevenly. Another model focuses on the powerful gravitational relationship between the young Earth and the nearby moon. When the moon orbited much closer than it does today, tidal flexing may have generated unequal heating inside its shell, subtly changing how quickly different regions solidified. A far more dramatic hypothesis suggests that Earth once had a second, smaller companion moon. Computer simulations show that a slow collision between the 2 moons could have spread material across one hemisphere rather than excavating a normal crater, building elevated terrain without completely melting the surface. Other researchers suspect that a giant early impact, deep internal circulation, or the uneven movement of heat-bearing material may have amplified an initial difference that began for another reason. Each idea can reproduce certain features, but none yet explains every observation at once. A successful theory must account for topography, internal temperature, chemical distribution, crustal structure, and the timing of ancient geological activity without contradicting the samples and orbital measurements already available. The difficulty is that many of these processes could have influenced one another. Uneven cooling might have redirected internal material, while an impact could have changed later heat flow, leaving scientists to separate the first cause from the consequences that followed. The moon's two faces may therefore be the result of several events acting in sequence rather than one perfect explanation. What appears to you as a simple visual contrast may actually be a frozen argument between competing histories, each written into the same ancient sphere. Colossal impact scar is hidden across the far side of the moon. The largest wound on the moon is so enormous that its complete shape becomes difficult to recognize when you look at the ground inside it. Known as the South Pole Aitken Basin, this ancient impact structure stretches for more than 2,500 kilometers, extending from the region near the lunar South Pole toward Aitken crater and occupying almost a quarter of the moon's circumference. Its floor lies, on average, about 10 kilometers below the surrounding terrain, while remnants of its elevated outer regions rise far above the basin's deepest areas. Yet it does not resemble a clean circular crater with a simple rim. The collision happened so early that billions of years of smaller impacts have shattered its boundaries, placed new craters inside it, and softened the clarity of its original form. Only when spacecraft measured elevation across the entire moon did the full scale of the depression become unmistakable. In color-coded topographic maps, the basin emerges as a vast low region surrounded by higher ground, like the faded imprint of a blow too large to fit within an ordinary landscape. The object that created it struck when the moon's surface was still young, releasing enough energy to reshape a substantial portion of the hidden hemisphere within a short geological moment. Rock was crushed, heated, displaced, and thrown across immense distances, while the crust beneath the impact site was compressed and reorganized. From Earth, you cannot see the basin spread openly across the lunar disk. At most, parts of its outer terrain can be glimpsed near the moon's southern edge, concealing the true dimensions of the structure behind the curve of the globe. This makes the scar strangely easy to overlook despite its size. Entire nations could fit across its width, yet it remained outside human knowledge until machines learned to map the moon as a complete world. The far side is often imagined as a collection of countless small craters, but beneath those individual marks lies evidence of something much greater, a single ancient collision that altered the shape of an entire hemisphere and left the moon carrying a wound too vast to be seen from any one place. The South Pole Aitken Basin may be one of the solar system's greatest wounds. A crater can be so violent that it stops behaving like a crater and begins reshaping an entire world. The South Pole Aitken Basin belongs to that rare class of impact scars, not simply because of its enormous reach, but because the collision disturbed the moon on several levels at once. The initial object would have struck at tremendous speed, compressing the ground into an intensely heated zone before the surface could move out of the way. For a brief moment, solid rock behaved less like an unchanging floor and more like a material capable of flowing, collapsing, and rebounding. The first cavity was probably much smaller than the final basin. As shattered crust slid inward and the surrounding landscape deformed, the affected region expanded until it became several times wider than the area originally excavated. This is why scientists call structures of this scale basins rather than ordinary craters. Their formation involves broad rings, deep fractures, collapsing walls, and changes extending far beyond the point of impact. The event also occurred extremely early, probably more than 4.3 billion years ago, placing it close to the beginning of the moon's preserved history. Determining its exact age could help researchers test whether the inner solar system experienced one sudden episode of intense bombardment or a longer, uneven decline in collisions. The basin is therefore both a wound and a clock. Its damaged rocks may record when large objects were still moving chaotically among the young planets, striking surfaces before the solar system settled into the quieter arrangement you know today. When you consider the basin this way, you are not merely looking at the aftermath of one asteroid. You are looking at a surviving fragment of an era when worlds were still being shaped through destruction, and when a single collision could permanently redirect the geological future of an entire hemisphere. The impact may have torn through the moon's crust and exposed its interior. Imagine discovering a natural doorway into the moon, opened not by drilling machines, but by an impact powerful enough to remove layers that had hidden its interior since formation. That possibility is one reason the South Pole Aitken region attracts such intense scientific interest. The moon is built in layers, with a lighter rocky crust resting above a denser mantle. Yet almost everything collected by the Apollo missions came from the surface of the near side, and represents only a limited part of that structure. A basin-forming collision can act like an enormous excavation, launching upper material outward while drawing deeper rock upward during the rebound that follows. Models of the South Pole Aitken impact suggest that the event may have cut through much of the crust and reached material originating near or within the mantle. Orbital instruments have detected rocks inside and around the basin that contain more iron-rich minerals than typical lunar highlands, and recent gravity studies have identified dense bodies near the basin's rim that may be pieces of mantle-rich ejecta buried within the crust. Yet scientists remain careful, because unusual material does not automatically prove that bare mantle lies exposed at the surface. Some readings could instead represent lower crust, ancient volcanic deposits, or a vast sheet of rock melted and chemically rearranged by the impact itself. Billions of years of later cratering have also mixed debris from many depths, turning the region into a geological puzzle whose pieces no longer rest where they began. This uncertainty is precisely what makes samples from the basin so valuable. A confirmed fragment of lunar mantle could reveal how the moon separated into layers, which minerals sank into its depths, and how much heat remained after its earliest molten stage. The impact may have torn open the moon's outer shell, but understanding what came through that opening requires more than seeing an unusual stone. It requires asking whether you are holding a piece of the surface, the deep crust, or material from a hidden interior that humanity has never directly touched. Strange gravitational anomaly lies beneath the giant hidden basin. Something buried beneath the South Pole Aitken basin pulls more strongly than the surrounding moon, even though nothing unusual rises above the surface to announce its presence. Scientists detected this hidden excess of mass by combining detailed topographic measurements with gravity data, including observations from NASA's Grail spacecraft. As an orbiter passes above denser underground material, the additional gravitational pull slightly alters its motion, allowing researchers to map structures that no camera can see. Beneath the basin, those measurements revealed an unexpected concentration containing more than 2 quintillion kilograms of extra mass and possibly extending deeper than 300 kilometers. This does not mean a single solid metal object is resting intact below the crater. Instead, the anomaly may represent material spread through a broad region of the lunar mantle. One explanation is that part of the metallic core of the ancient impactor remained mixed into the moon rather than sinking completely toward its center. Computer models show that iron from a sufficiently large asteroid could remain suspended within the mantle after the surrounding rock cooled. Another possibility is that the impact pushed dense lunar mantle upward beneath the basin, replacing lighter crustal material and producing a stronger local gravitational field. Researchers have also considered whether the enormous pool of impact-melted rock cooled and separated into layers, allowing heavier minerals to concentrate below. Each explanation tells a different story. One preserves a portion of the object that struck the moon, another reveals how the moon's own interior rebounded, and a third records how a temporary ocean of molten stone crystallized after the collision. The anomaly is therefore not merely a mysterious weight underground. It is evidence that the violence of an impact can continue shaping gravity long after heat, movement, and sound have disappeared. The surface above may appear silent and ancient, yet spacecraft passing overhead can still feel the invisible architecture left behind by an event more than 4 billion years ago. The far side may preserve some of the oldest material left on the Moon. Some of the Moon's earliest surviving history may still be locked inside pale rocks scattered across the hemisphere, hidden from Earth. Soon after the Moon formed, much of its outer region was probably a vast ocean of molten stone. As this magma slowly cooled, dense minerals sank, while lighter crystals rich in a mineral called plagioclase floated upward, gathering into a primitive crust dominated by a bright rock known as anorthosite. Parts of the far side highlands may preserve fragments of that first crust more clearly than many younger or more heavily altered regions elsewhere. This does not mean the rocks have remained peacefully untouched. Countless impacts have shattered them, buried them, lifted them again, and welded broken pieces into new rocks called breccias. Even so, an ancient fragment can retain chemical ratios and mineral structures inherited from the Moon's earliest cooling stage. Orbital instruments search for unusually pure exposures of anorthosite, while fresh craters occasionally excavate material that was protected beneath the weathered surface. These exposures could help scientists determine how quickly the lunar magma ocean cooled, whether the first crust formed evenly, and how soon the young Moon separated into its internal layers. A rock does not need to preserve its original shape to preserve its original information. Even a damaged crystal can carry a clock within its atoms. The far side may therefore contain more than old ground. It may hold surviving pieces of the moment when a molten world first developed a solid skin, allowing you to look at a broken stone and ask whether you are seeing not merely part of the Moon, but one of its earliest memories. Why the hidden hemisphere is covered with so many more visible craters. The most revealing word in the phrase "more craters" is not more, but visible. The far side was not necessarily struck by vastly more objects than the hemisphere facing Earth. Instead, much of its surface has retained a clearer record of the impacts it received. Every exposed landscape accumulates craters over time, so an older surface generally carries more of them than a younger one. Scientists use this principle through a method called crater counting, comparing the number and size of impact marks across different regions to estimate their relative ages. On the far side, extensive ancient terrain remained exposed for immense periods without being broadly replaced by younger surface material. New impacts therefore continued to appear on top of old ones. Some craters cut across earlier rims, while others formed inside basins that were already ancient, creating layers of damage that can be read in sequence. Large collisions also launched fragments back into the sky, and those fragments returned to produce clusters and chains of secondary craters, multiplying the visible complexity of the landscape. Eventually, a surface can become so crowded that each new crater partly destroys an older one, creating a condition called crater saturation. The far side contains regions approaching this heavily worked state, where almost no patch of ground has escaped modification. Its crater density is therefore not a simple counter-recording how many rocks fell from space. It is the combined result of age, preservation, overlapping impacts, and the limited removal of earlier scars. When you see thousands of circles pressed into the hidden hemisphere, you are not looking at random decoration. You are seeing time expressed as accumulated damage, with every surviving rim marking a moment the surface was struck and failed to forget. The far side records billions of years of impacts that Earth has erased. Earth has endured an ancient storm of collisions, yet the living planet beneath your feet has destroyed most of the evidence. Small incoming objects often burn, fragment, or slow within the atmosphere before reaching the ground, while larger craters that do form must survive rain, rivers, oceans, glaciers, wind, plant growth, sediment, and changing temperatures. Beneath all of this, plate tectonics continually moves and recycles the crust. Old seafloor sinks into the mantle, mountains rise and erode, volcanic material covers earlier landscapes, and impact structures can be folded, buried, or pulled apart until only subtle geological traces remain. The Moon offers a radically different archive. It has no thick atmosphere, no oceans, no flowing rivers, and no global system of moving plates capable of renewing its exterior. Its craters slowly soften under micrometeorite impacts and can be damaged by later collisions, but many large structures remain recognizable after billions of years. Because Earth and the Moon have traveled through nearly the same region of space, lunar scars help scientists estimate how the impact rate changed throughout the history of the inner solar system. Researchers can study crater populations, connect some surfaces to dated rocks, and use that timeline to infer periods when Earth may also have experienced heavier bombardment. The Moon cannot show exactly where every object struck our planet, but it preserves the wider rhythm of collisions that affected both worlds. In this sense, the far side is not only lunar ground, it is a surviving witness to chapters of Earth's past that erosion and geology have almost completely removed. The quiet landscape above you remembers events your own planet was too active to keep. Why the Moon's hidden highlands look brighter, rougher, and more ancient. The far side's brightest regions are not glowing with their own light. They are revealing a landscape that has remained elevated, fractured, and exposed for an extraordinary length of time. These vast areas are known as the lunar highlands, and they rise above the lower terrain that dominates many other parts of the Moon. Their lighter appearance comes partly from pale, feldspar-rich material that reflects more sunlight than darker volcanic rock, but brightness alone does not explain their ancient character. The highlands are filled with steep walls, broken ridges, overlapping depressions, and irregular blocks created by repeated impacts. Each collision shattered the ground, lifted buried material, and spread debris across the surrounding surface. Over billions of years, this process produced a rough landscape in which there are few broad, uninterrupted plains. Sunlight striking such uneven ground creates sharp contrast between illuminated slopes and deep shadows, making the terrain appear even more dramatic from orbit. Scientists can estimate the relative age of these regions by examining how densely the surface has been modified and how later structures cut across earlier ones. A younger landscape tends to hide or replace older features, while the far side highlands preserve complicated sequences in which one geological event is written over another without completely erasing it. Their brightness therefore belongs to their minerals, their roughness belongs to repeated destruction, and their ancient appearance belongs to long preservation. When you look across these pale uplands, you are not seeing a surface frozen exactly as it was at birth. You are seeing an old foundation that has been broken, rearranged, and exposed so many times that its damage has become the clearest evidence of its age. The far side may still carry scars from the solar system's most violent era, long before the planets followed the relatively stable paths you know today. The inner solar system may have been crossed by far more wandering debris than it is now. Asteroids and leftover planetary fragments moved through changing orbits, and some models suggest that the giant planets themselves shifted positions, disturbing smaller bodies and sending part of that material toward the inner worlds. The exact timing and intensity of this violent era remain debated. One idea proposes a concentrated rise in major impacts roughly 4 billion years ago, often called the Late Heavy Bombardment, while another view suggests that collisions simply declined gradually from an earlier and even more chaotic period. The far side may help scientists distinguish between these possibilities because some of its largest and most damaged structures formed during those distant intervals. Their rims have been broken, their floors altered, and their outlines partly buried, yet the sequence in which they overlap can still reveal which events came first. Rocks melted by major collisions may also contain minerals whose internal clocks were reset by extreme heat, allowing future samples to place certain impacts within a clearer timeline. This matters because the same bombardment affected more than the Moon. It may have influenced the early surfaces of Mercury, Mars, Venus, and Earth, possibly changing environments in which water, atmosphere, and eventually life developed. The scars on the far side are therefore not merely evidence of local destruction. They may preserve the rhythm of a solar system still settling into order. By learning when those ancient blows occurred, you begin to see planetary stability not as the natural starting point, but as something that emerged slowly from violence after countless objects had already been shattered, displaced, or absorbed into the worlds that survived. The chemical composition of the far side is different from the side facing Earth. The Moon's two hemispheres do not merely look different from above. Their rocks contain noticeably different chemical signatures. Orbiting spacecraft have discovered this by measuring the energy released from the surface in several ways, including gamma rays, neutrons, and reflected sunlight. These observations reveal the distribution of elements and minerals across regions that cannot be sampled directly. The near side contains an unusually large province rich in potassium, phosphorus, thorium, and rare earth elements, a mixture often grouped under the name creep. Much of this material is concentrated around Oceanus Procellarum and nearby basins, making the visible hemisphere chemically distinctive on a planetary scale. Across most of the far side, those heat-producing elements are much less abundant. The hidden hemisphere is instead dominated by extensive feldspathic highland material, although some enormous basins expose rocks richer in iron and other minerals associated with greater depth. Titanium also varies strongly from place to place, showing that even dark-looking rocks did not all come from identical magmas. These chemical maps allow scientists to reconstruct processes that happened while the Moon was still differentiating internally. As its early molten material crystallized, some elements entered common minerals, while others remained concentrated in the last portions of liquid. If those leftovers gathered unevenly, they could have created long-lasting regional differences in internal heat and rock formation. Yet the measurements do not provide a simple answer, because later impacts mixed material from separate depths and transported debris far from its source. The far side is chemically different, but it is not chemically uniform. Its composition forms a patchwork of ancient crust, excavated interior rock, and redistributed fragments. Reading that patchwork is like tracing how the young Moon separated its ingredients before its surface became quiet, revealing that two hemispheres of one world can inherit different internal histories without ever becoming separate worlds. Missing radioactive elements may explain why the far side never flooded with lava. The missing ingredient on the far side may not have been lava itself, but the invisible heat required to keep producing it. Deep within rocky worlds, certain forms of potassium, uranium, and thorium slowly release energy as they decay, acting like countless microscopic heaters buried inside the planet. On the Moon, many of these heat-producing elements became concentrated in material left over during the final stages of its early internal cooling. Much of that material appears to have gathered beneath the near side, where its continuing warmth may have helped sections of the mantle remain capable of partially melting for longer periods. Magma does not simply appear because a large basin exists above it. Underground rock must become hot enough to melt, and the resulting liquid must remain mobile long enough to rise. If much of the far side interior contained fewer radioactive heat sources, it may have cooled more quickly and produced less melt capable of reaching the surface. Recent gravity research supports the idea that part of the near side mantle stayed unusually warm because heat-generating elements were concentrated there, helping sustain volcanic activity long after other regions had become less active. This explanation must still be treated as part of a larger story rather than a final answer. The far side was not completely volcanic, and radioactive elements alone cannot determine where an eruption occurs. Pressure, mineral composition, fractures, and the movement of material inside the Moon also matter. Yet the uneven distribution of internal heat offers a powerful reason why two regions of the same world could respond so differently over time. The broad absence of lava plains may therefore represent an energy shortage preserved in stone, not a hemisphere where molten rock never existed, but one where the hidden furnace weakened too early to transform most of the surface above it. The hidden hemisphere could reveal how the moon's first crust was formed. Before the moon possessed a single crater, it faced a quieter but equally dramatic transformation. It had to build its first solid surface from a body that was still largely molten. As the young lunar interior cooled, minerals did not all crystallize and move in the same way. Dense crystals containing minerals such as olivine and pyroxene tended to descend into the liquid below, gradually contributing to deeper layers, while buoyant crystals rich in plagioclase rose toward the top. The great unanswered question is how those floating crystals became a planetary crust. They may have collected into separate rafts that collided, thickened, cracked, and eventually joined together, rather than forming one smooth shell at the same moment everywhere. Some crystals may have been trapped within slowly cooling magma, while others were compressed, remelted, or mixed with the final chemically unusual liquids left behind. This means the earliest crust was probably not a perfect layer, but a developing structure full of regional differences from the beginning. The far side could help researchers test this, because it contains extensive exposures of ancient anorthositic material, including locations where orbital instruments have identified rock that may be unusually rich in plagioclase. By comparing its mineral purity, crystal textures, trace elements, and ages, scientists can investigate whether the first crust formed rapidly or in several stages, whether it was globally similar before later events altered it, and whether the hemispheric divide began while the magma ocean was still crystallizing. Even the absence of certain minerals can be informative, revealing which crystals had already sunk or which late liquids had not yet arrived. The hidden hemisphere is therefore more than a surviving piece of old terrain. It may be the best remaining laboratory for reconstructing the moment when the moon stopped being an exposed ocean of magma and began becoming a world with a surface, a boundary, and a geological history of its own. From most of the far side, Earth never appears in the sky. Step onto the central far side and the most unsettling object in the sky would be the one that never appears, Earth. From that location, our planet would remain permanently below the lunar horizon, not temporarily hidden by night or weather, but geometrically absent from every moment of your stay. The sun would still move slowly across the sky, and stars would rise and set as the moon continued through its long cycle of daylight and darkness. Yet the blue world where every human life began would never climb into view. This makes the lunar sky profoundly different from the sky imagined in many paintings and films. The famous Earthrise photographed by Apollo 8 was seen from a spacecraft moving around the moon. An observer standing at a fixed site near the center of the far side would not watch Earth rise in the same way. Only regions near the boundary between the near and far hemispheres can occasionally gain a limited view as the moon's slight apparent rocking changes the exact direction of Earth. From most deeper far-side locations, the landscape itself blocks the planet completely. You could look across grey ridges beneath a black sky and know that Earth was physically close by astronomical standards, yet receive no visual confirmation of it. There would be no blue disk to indicate home, no clouds to suggest weather, and no changing continents to remind you that billions of lives continued beyond the horizon. The absence would alter your sense of direction as much as your emotions, because on much of the moon's visible side, Earth serves as an almost stationary landmark in the sky. On the hidden hemisphere, that landmark is replaced by emptiness. You would not feel that Earth had vanished from the universe. You would understand that an entire world can remain nearby, gravitationally present and filled with life, while being completely excluded from sight by nothing more mysterious than the curve of the ground beneath your feet. What it would feel like to stand where Earth is permanently below the horizon. The deepest loneliness on the moon might not come from the silence, but from knowing that your entire world is nearby and still impossible to see. Standing in the central far side, you would find yourself beneath a black sky where the stars remain sharp even during daylight, because there is no atmosphere to scatter sunlight into blue. The ground would feel unnaturally light beneath your boots, allowing each step to carry you farther and keep you suspended longer than the same movement on Earth. Yet the landscape would offer almost no response to your presence. Dust would fall without drifting in air. Your footsteps would create no sound outside your suit, and even a nearby impact would reach your ears only through vibrations traveling through the ground or your equipment. The only sounds would come from within: your breathing, the movement of fabric, the hum of pumps, and perhaps the quiet voice of another explorer transmitted through a headset. On the near side, Earth could serve as a fixed emotional landmark, a bright reminder of oceans, weather, cities, and everyone you have ever known. Here, that landmark would be missing. You could climb a ridge and still find no blue light waiting beyond it. Every familiar place would remain concealed behind the moon's solid body, close enough for radio signals to reach in little more than a second when a relay path existed, yet visually farther away than any star. Lunar daylight would continue for many Earth days, causing exposed ground to become intensely hot, and then a long night would remove the sun and allow the surface to become brutally cold. Without wind, clouds, moving water, birds, or vegetation, change would occur slowly, mostly through shifting sunlight and your own movement. Psychologically, the absence of Earth might alter your sense of belonging. Home would no longer be a place above you. It would become an idea beneath the horizon, reconstructed from memory. You might understand more clearly than ever that seeing something is not necessary for depending on it. Every breath, every tool, every instruction, and every hope of returning would still originate from that hidden planet. Standing there would not make Earth less real. It might make its presence feel more powerful, because you would be surrounded by a universe full of visible light, while longing most intensely for the one world the sky refused to show you. Spacecraft vanish from direct contact with Earth behind the moon. Or no, spacecraft does not need to travel far from Earth to disappear completely from the people controlling it. It only needs to pass behind the moon. Radio communication usually requires a clear path between the transmitting spacecraft and a receiving antenna, and the moon's enormous body blocks that path when a vehicle moves across the hidden half of its orbit. The signal cannot simply curve around thousands of kilometers of solid rock, so voices, commands, tracking information, and scientific data stop reaching Earth directly. From a control room, the disappearance can feel dramatic, but nothing may be wrong with the spacecraft. Its engines can continue operating, its computers can keep following stored instructions, and its instruments can continue collecting observations, while the ground receives only silence. This forces mission planners to treat every communication blackout as a period of independence. Before the vehicle crosses the boundary, commands must already be loaded, navigation estimates checked, and automatic safety systems prepared to respond if temperatures, power levels, or orientation move outside acceptable limits. The spacecraft may store measurements in onboard memory and transmit them later when Earth returns to its line of sight. During historic crewed lunar flights, this loss of contact became a repeated and expected part of each orbit. Astronauts entering the far side could no longer speak with mission control, and controllers had to wait for the spacecraft to emerge at the predicted time. If it appeared late, the silence gained a different meaning, because a planned engine burn performed behind the moon might have changed the orbit or failed entirely. The first radio call after reappearance therefore served as more than a greeting. It confirmed that the spacecraft had survived an interval during which no one on Earth could watch, advise, or intervene. This reveals an important truth about spaceflight. Communication is not an invisible convenience, but part of the vehicle's survival system. When the moon moves between a spacecraft and Earth, the machine has not entered another universe, yet operationally, it has crossed into a temporary world of its own, where every decision must be made by the crew, by automation, or by instructions sent before the door of radio contact closed. why every far-side mission needs a satellite to speak for it. To place a working machine on the lunar far side, engineers must first place a second machine where both worlds can hear it. A lander sitting deep within the hidden hemisphere has no direct radio view of Earth, so any mission requiring regular communication needs a relay spacecraft or an equivalent network positioned above the obstruction. The relay acts as a translator and messenger rather than merely amplifying a weak signal. It receives commands from antennas on Earth, stores or processes them when necessary, and transmits them toward the lander or rover. Scientific measurements, photographs, engineering reports, and location data travel back along the same two-part route. Choosing the relay's position is difficult because it must maintain useful visibility of both the surface mission and Earth while remaining stable enough to conserve fuel. China solved this problem for the Chang'e 4 landing by launching Keqiao before the lander, placing the relay in a looping orbit beyond the moon's far side where it could bridge the otherwise impossible connection. Later relay systems, including Keqiao 2 and proposed international lunar communication networks, are designed to support more locations and reduce periods without coverage. A relay can also provide navigation assistance, precise timing, and links between several vehicles, functions that become increasingly important when rovers travel beyond local terrain, or astronauts depend on rapid contact during emergencies. Yet the relay introduces another point of vulnerability. Its antennas must remain correctly aimed, its power system must survive, and its orbit must be maintained. A surface vehicle could remain mechanically healthy while becoming effectively isolated if the relay failed. Future far-side exploration will therefore require redundancy, several satellites, overlapping communication paths, stored emergency procedures, and enough autonomy for crews or robots to continue operating during interruptions. The first thing a far-side mission needs is not a drill, a camera, or even a wheel. It needs a voice placed high above the horizon. Only after that artificial bridge exists can a silent machine on hidden ground become part of a human mission, rather than an unreachable object sending signals into stone. The far side may be the quietest radio environment near Earth. There is a place near Earth where the modern world can almost disappear from the radio spectrum, and it lies on the hemisphere of the moon that never faces us. Our planet continuously leaks electromagnetic signals into space from television transmitters, radar systems, navigation networks, aircraft, military installations, mobile communications, and countless satellites. Even remote observatories on Earth cannot escape this activity completely. Because weak human-made transmissions can travel great distances and overwhelm the delicate cosmic signals astronomers are trying to measure, the far side offers something extraordinarily rare, a naturally isolated environment located close enough for practical exploration, but distant enough from direct terrestrial interference to become one of the quietest available sites in the inner solar system. Its advantages extend beyond separation from cities. The moon has no dense atmosphere and no active ionosphere like Earth's, so low-frequency radio waves are not repeatedly bent, absorbed, or reflected by layers of electrically charged air above the telescope. During the lunar night, an observatory can also avoid direct solar radio interference, creating periods when both Earth and the Sun are less disruptive. Yet quiet does not mean perfectly silent. The universe itself produces radio noise. Energetic particles interact with equipment, and future spacecraft operating near the moon could contaminate the environment with their own transmissions. Even cables, computers, power converters, and motors belonging to the observatory could create interference unless they were carefully shielded. This is why scientists discuss protecting the far side as a radio quiet zone before growing lunar activity fills it with artificial signals. Humanity has spent more than a century making the space around Earth increasingly loud, often without noticing because radio noise cannot be heard by human ears. The hidden hemisphere offers a rare chance to preserve a different kind of wilderness. Not an untouched forest or ocean, but a region of electromagnetic stillness, where the faintest natural whispers might remain detectable. Its value may depend on whether we can reach it without destroying the silence that made the journey worthwhile. The moon's body shields its hidden side from humanity's constant radio noise. The moon becomes a shield, not because its surface absorbs every radio wave, but because thousands of kilometers of solid rock stand directly between Earth and much of the far side. Most radio communication travels approximately along a line of sight, so a transmission leaving our planet cannot pass straight through the lunar body to reach an antenna positioned deep within the hidden hemisphere. The signal strikes the Earth-facing side, scatters, reflects, or is absorbed, while the region behind the moon falls into an electromagnetic shadow. This protection is strongest near the center of the far side, where an observatory sits farthest below the radio horizon and is surrounded by the greatest amount of blocking terrain. Closer to the edges, some signals can leak around the moon through diffraction, a process in which long radio waves bend slightly around obstacles. The amount of leakage depends on frequency, geometry, local topography, and the position of the transmitter. Mountains and crater walls can provide additional shielding, which is one reason deep farside craters are attractive locations for sensitive instruments. The protection is also not guaranteed against transmitters that are no longer on Earth. A satellite orbiting high above the moon, a navigation beacon positioned beyond its edge, or a communication relay visible from both hemispheres could send interference directly into the supposedly quiet region. Future lunar infrastructure therefore creates a difficult balance. Farside missions require communication systems, yet those same systems could disturb the observations that make the far side scientifically unique. Engineers may need to limit transmission power, reserve protected frequencies, coordinate operating schedules, and place antennas where their signals avoid sensitive telescopes. The moon provides the natural wall, but preserving the shadow behind it will require human discipline. You may think of silence as the absence of activity, yet here it is produced by geometry. One celestial body standing in exactly the right place to hide a listening instrument from an entire technological civilization. A telescope there could hear signals from the universe's earliest dark ages. Hidden inside the faint radio glow of space may be a message sent before any star had begun to shine. After the early universe cooled enough for protons and electrons to form neutral hydrogen, but before the first generations of stars filled space with visible light, the cosmos entered a long interval called the Dark Ages. It was not empty. Vast clouds of hydrogen were slowly gathering under gravity, carrying the first subtle outlines of the galaxies and clusters that would appear later. Neutral hydrogen can absorb or emit radiation at a characteristic wavelength of about 21 centimeters. And as the universe expands, those ancient waves are stretched to much longer wavelengths and much lower radio frequencies before reaching us. In principle, measuring this signal could reveal how cold the early gas became, how matter gathered into structure when the first stars began heating their surroundings, and how the first luminous objects transformed neutral hydrogen into ionized gas. From Earth's surface, much of this frequency range is extremely difficult or impossible to study. The ionosphere distorts low-frequency waves and blocks the lowest portions entirely, while human transmissions can be millions of times stronger than the cosmological patterns scientists seek. A far-side telescope would escape these two major barriers, especially during the lunar night, when the moon could also block direct radio outbursts from the sun. The instrument might use many simple antennas spread across the ground rather than one familiar dish, combining their measurements to separate the weak hydrogen signature from the much brighter radio foreground produced by our own galaxy. Even in this protected environment, the task would be extraordinarily difficult. The desired signal is faint, the lunar temperature changes are severe, and every electronic component could create noise of its own. But success would open a chapter of cosmic history that ordinary telescopes cannot photograph, because there were no stars available to illuminate it. You would not be seeing the first objects directly. You would be listening to the hydrogen around them change as darkness slowly prepared to become light, recovering the hidden transition between a nearly featureless young universe and the first cosmic dawn. The first spacecraft to land on the far side entered a world no mission had touched. The first machine to settle onto the moon's far side did not merely reach a new coordinate, it crossed a boundary that every previous lunar landing had left untouched. On January 3, 2019, China's Chang'e 4 spacecraft descended into Von Karman crater, a vast depression about 186 kilometers wide within the larger South Pole Aitken region. Unlike the relatively open plains chosen for many earlier landings, this destination lay inside an ancient, heavily modified landscape where crater walls, buried debris, scattered rocks, and uneven ground created serious hazards. During the final descent, the lander had to reduce its speed, examine the terrain beneath it, avoid dangerous obstacles, and select a safe point without a pilot physically controlling each movement in real time. When its legs finally met the surface, no previous spacecraft had ever operated from the lunar ground there. Soon afterward, the Yutu-2 rover rolled down a pair of ramps and began exploring a place known before then mainly through orbital images. Its cameras returned close views of angular stones, shallow craters, fine dust, and a horizon no lander had photographed from below. Instruments examined the surface composition and used radar pulses to investigate layers hidden beneath the rover, turning an untouched landing site into a geological laboratory. The meaning of untouched must be understood carefully. The terrain had been altered for billions of years by impacts, radiation, and solar particles, and earlier orbiters had mapped it from above. What was new was direct physical investigation from the surface. For the first time, wheels pressed tracks into far-side soil. Instruments measured the environment from within it, and a stationary lander watched the sun move across a horizon that no earlier mission had occupied. The achievement quietly changed the geography of exploration. A region that had existed only as distant terrain became a place where a machine could stop, look around, choose a path, and continue. You can imagine that first view not as the discovery of a supernatural world, but as something more honest and perhaps more powerful. The moment a familiar moon became larger because humanity had finally learned how to stand on the half it had never reached. The first samples from the far side came from a region unlike any visited before. When the first far side material arrived on Earth, it carried the history of a lunar province that had never before been represented inside a laboratory. China's Chang'e 6 mission landed on June 2, 2024, in a dark volcanic plain within the southern part of Apollo Basin, itself nested inside the immense South Pole Aitken Basin. This geological setting made the collection fundamentally different from every earlier lunar sample return. The Apollo astronauts, the Soviet lunar probes, and China's Chang'e 5 mission had all brought material from the hemisphere facing Earth, mostly from regions belonging to geological and chemical provinces, unlike the deep far-side basin selected for Chang'e 6. The new mission used both a scoop and a drill, allowing it to collect loose surface soil, as well as material from slightly below the uppermost layer. Its return capsule reached Earth on June 25th, carrying 1,935.3 grams of lunar material. The grains were not all created in one event or even in one place. Preliminary analysis showed that the collection contains local basalt produced by volcanic eruptions, mixed with lighter non-volcanic fragments delivered by impacts from surrounding terrain. This mixture is scientifically valuable because the surface of the moon is constantly stirred by collisions. A single container can therefore include pieces of local lava, distant highland crust, impact glass, and fragments excavated from levels no longer exposed nearby. The Apollo Basin also lies within a structure so large and ancient that debris related to several stages of lunar history may have been deposited across the landing area. Scientists must now separate those overlapping stories grain by grain, identifying which particles formed from local magma and which arrived as ejecta from older impacts. That complexity does not weaken the samples. It gives them depth. Earlier collections taught humanity an enormous amount, but they came from only one broad side of a chemically divided moon. Chang'e 6 supplied the first physical comparison from the other side. The grey soil inside its container may look almost ordinary, yet it came from a geological environment no Apollo astronaut walked across and no earlier return mission sampled, finally allowing the hidden hemisphere to speak through matter rather than images alone. Why rocks from the moon's hidden side could rewrite the story of its birth. Few ancient crystals can force scientists to reconsider the childhood of an entire world, because rocks preserve events that no camera could ever have witnessed. The leading model of lunar origin proposes that a tremendous collision struck the young Earth and produced a disk of heated debris from which the moon formed. That explanation describes the beginning, but it does not settle what happened next. Researchers still debate how thoroughly the debris mixed, how much water and other volatile material survived, how quickly the newborn moon cooled, and whether its interior developed as one globally connected system or became uneven almost immediately. Farside samples offer an independent test because most previous conclusions were built from rocks gathered within a limited set of near-side environments. In the laboratory, scientists can examine oxygen and other isotopes, date microscopic mineral grains, measure traces of water, study the chemistry of volcanic fragments, and search for minerals that originated deep within the lunar mantle. Each measurement addresses a different stage of development. Isotopic similarities can reveal connections between Earth and lunar material. Ancient crustal fragments can test how a global magma ocean crystallized. Primitive mantle minerals can show what the interior was like before repeated melting altered it. Volcanic rocks reveal how long internal heat survived, and whether farside magma came from a source unlike the material already known from Apollo samples. Early Chang'e 6 studies have dated much of the sampled basalt to about 2.83 billion years ago, found evidence consistent with a global lunar magma ocean, and suggested that the enormous basin-forming collision may have modified the mantle beneath the hidden hemisphere. Other work has identified unusually primitive olivine and indications that the far side mantle may differ in water content and oxidation state from better sampled near-side regions. None of these findings means one bag of soil has already replaced the established origin story, and responsible science does not turn every difference into a revolution. The deeper possibility is more subtle. The broad outline of the moon's birth may remain correct while its timing, internal mixing, cooling sequence, and hemispheric development require major revision. You may discover that a world can share one beginning yet divide into unequal histories almost at once. In that sense, these rocks do not simply tell us where the moon came from. They ask whether we have been describing a whole world after studying material from only half of it. The first rocks ever collected from the far side came from a place unlike any Apollo landing site. For the first time, lunar rocks reached Earth from a landscape that no Apollo astronaut had ever approached, and the difference begins with geography before it reaches geology. All 6 Apollo landing sites were placed on the moon's near side, relatively close to the equator, where direct communication with Earth, manageable lighting, and well-mapped terrain made human landings safer. Those missions still explored an impressive variety of environments. Apollo 11 and Apollo 12 sampled dark volcanic plains. Apollo 15 examined the boundary between Mare Imbrium and the Apennine Mountains. Apollo 16 visited bright highland terrain, and Apollo 17 explored a valley beside Mare Serenitatis. Yet none entered the South Pole Aitken region, and none collected material from inside a basin nested within that enormous far-side structure. Chang'e 6 landed in the southern part of Apollo Basin, where a volcanic plain lies among ancient impact deposits that may have traveled from the basin walls, surrounding highlands and deeper layers excavated by later craters. The soil was therefore not expected to represent a single clean rock unit. Lunar dust is continuously stirred by impacts, so the returned container holds a geological mixture. Fragments of local basalt, impact glass, welded debris, pale crustal grains, and particles thrown into the landing area from distant sources. This differs from Apollo not because the astronauts gathered simple or unimportant material, but because their samples came from a different hemisphere, with a different geological setting and a separate chain of major impacts. Laboratory instruments can now compare rocks collected directly from both sides, rather than trying to infer the hidden hemisphere entirely from orbital measurements. Researchers can examine how the minerals crystallized, determine when individual fragments formed, and trace whether some grains originated locally or arrived as ejecta. A tiny particle may have begun inside a volcanic flow, within an old crater wall, or beneath a surface later shattered by another collision. The first far-side collection is therefore valuable not merely because it came from somewhere new, but because it breaks a sampling imbalance that shaped lunar science for more than half a century. Apollo gave humanity extraordinary chapters of the moon's story, but Chang'e 6 opened a volume written in a region whose rocks had never before been placed beside them on an Earth laboratory table. China's Chang'e 6 mission reached one of the moon's most ancient hidden regions. Chang'e 6 landed on ground where several different ages of the moon are stacked together, with comparatively younger lava resting inside scars created when the solar system was still in its violent youth. Its destination was not simply the far side, but a carefully selected area within Apollo Basin, a roughly 490-kilometer impact structure formed inside the much older South Pole Aitken Basin. Scientists estimate that South Pole Aitken formed about 4.3 billion years ago, while Apollo Basin may date to roughly 3.9 to 4.1 billion years ago. The dark volcanic material covering parts of the landing region is younger still, and returned basalt fragments have been dated to about 2.8 billion years. This layered chronology makes the site unusually rich. The visible ground may belong mainly to an ancient lava plain, but nearby craters have excavated and scattered material from below it, while debris from the Apollo-forming collision and possibly the older South Pole Aitken event may also be mixed into the soil. Chang'e 6 therefore reached a location where one scoop could contain pieces representing widely separated chapters of lunar history. Mission planners had to balance that scientific promise against the practical dangers of landing. A region filled with small craters, slopes, blocks, and uneven deposits could offer valuable samples while threatening the spacecraft during descent. The chosen zone contained broad areas gentle enough for landing, but remained close to geological boundaries where different materials could be delivered into reach. After touching down on June 2, 2024, the spacecraft used surface sampling equipment and a drill before launching the collected material from the far side, an operation that required autonomous control and communication through a relay system. Yet the deeper accomplishment was geological rather than mechanical. The mission did not return an untouched piece of one ancient surface, because no exposed lunar terrain remains perfectly undisturbed. Instead, it entered a natural archive in which impacts had repeatedly opened older pages and mixed them into younger soil. The site is ancient, not because every grain formed at the same early moment, but because the landscape preserves access to structures created near the beginning of lunar history. Chang'e 6 reached a place where a relatively young volcanic layer sits over a succession of buried catastrophes, allowing scientists to study how the moon changed without losing all contact with what existed before. Farside samples may reveal whether the moon's two faces formed differently. The most important question carried home by the farside samples may be deceptively simple. Were the moon's two faces different from the beginning? Or did they become different only after sharing the same birth? Orbital observations already show strong contrasts in crust, elevation, volcanic coverage, and the distribution of heat-producing elements. But remote sensing cannot always determine when those differences appeared. Rocks can. If ancient crustal fragments from both hemispheres formed from a similar global reservoir, their minerals and isotopic patterns should preserve evidence of a shared early magma ocean. If they reveal separate chemical reservoirs at extremely early ages, the hemispheric divide may have begun while the Moon was still cooling and building its first crust. Chang'e 6 results have already added an important piece to this debate. Studies of its basalt support the idea that a global magma ocean once affected the entire Moon, suggesting that the two hemispheres did not begin as completely unrelated geological systems. At the same time, differences in lead isotope evolution indicate that parts of the far side interior followed a distinct path after that early molten stage. This raises the possibility that the Moon began with a broadly shared structure and later diverged as impacts. Internal heat, mantle circulation, and uneven concentrations of chemical elements altered each hemisphere differently. Researchers can test this by comparing the ages and compositions of far-side basalt with near-side volcanic rocks, examining whether their source regions contained similar amounts of water and heat-producing material, and searching for old crustal grains whose chemistry predates the later volcanic activity. They must also separate original differences from changes caused by the South Pole Aitken impact, which may have heated, excavated, and chemically modified a vast portion of the hidden mantle. A far-side sample can therefore answer one question while creating another. Does an unusual composition represent the Moon's earliest asymmetry, or the aftermath of a colossal collision? Only multiple minerals, ages, and sample locations can gradually separate those possibilities. The emerging story may be neither that the Moon was born with two completely different faces, nor that both sides remained identical for billions of years. It may be that one shared beginning contained small imbalances, and later events magnified them until the hemispheres became dramatically unlike each other. These rocks allow you to ask not merely why the two faces are different today, but at what moment one Moon began living two geological lives. Some rocks on the hidden side may have been thrown up from deep beneath the crust. A stone resting quietly on the far side may have begun its existence many kilometers below the place where it now lies. Large lunar impacts do more than press holes into the surface. They briefly turn solid rock into a moving system of compressed, fractured, and rapidly displaced material. As the impact cavity opens, rock is driven downward, swept outward, and then launched above the ground as ejecta. The deepest material is not always thrown the farthest, and much of it may become mixed with shallower debris before falling back around the crater. In large, complex craters, another process follows almost immediately. The crushed floor rebounds upward after the pressure is released, lifting deep rock into a central mountain or a ring of peaks. These structures act like natural drilling operations, bringing material into view that would otherwise remain sealed beneath the Moon's surface. Spacecraft have detected olivine-rich exposures near the edges of several major lunar basins, and because olivine is expected to be important in the lower crust or mantle, some researchers interpret these deposits as material excavated from unusual depth. That interpretation is promising but not certain. Olivine can also occur in intrusive igneous rocks within the crust, while impacts can melt, mix, and chemically alter several layers at once. A dark fragment found beside a crater may have come from deep underground, from a buried volcanic unit, or from a distant impact whose debris crossed hundreds of kilometers before landing there. Scientists therefore study mineral composition, crystal structure, surrounding geology, and the direction of ejecta patterns before assigning a source. The far side is especially valuable because its great basins and complex craters expose numerous levels of lunar material, sometimes placing ancient interior rocks beside younger debris at the surface. What appears to be a random field of stones may actually be a displaced vertical map of the Moon, with pieces from different depths scattered horizontally across the ground. To understand one of those rocks, you must ask not only what it is, but how violently it had to travel before a hidden layer became something sunlight could touch. The far side is not completely without lava plains, but they are surprisingly rare. The far side breaks its own geological pattern in a handful of places, where isolated patches of dark volcanic ground appear among overwhelmingly brighter terrain. These exceptions matter because they prove that the hidden hemisphere was never entirely sealed against eruption. Mare deposits exist there, but they are smaller, more scattered, and far less dominant than the connected volcanic plains visible from Earth. Across the whole Moon, mare account for roughly 16% of the surface, while about 30% of the near side is covered by them. Only a small share lies fully within the far side hemisphere. Many of those distant deposits occupy the lowest interiors of old impact structures, where enormous collisions weakened the crust and created depressions into which magma could later rise. Their shapes are often controlled by the basins containing them, rather than by wide volcanic provinces extending freely across the landscape. Some are partly hidden beneath younger ejecta, while others are so limited that early low-resolution photographs could easily miss them. Modern orbital cameras, elevation maps, thermal measurements, and spectral instruments have revealed small basaltic units that differ in age and composition, showing that far-side volcanism occurred in several episodes rather than through one brief event. The rarity of these plains also gives scientists a useful comparison. Each isolated deposit becomes a test of what special conditions allowed magma to escape there when neighboring regions remained unchanged. A local fracture may have opened after an impact. The crust may have been unusually thin beneath one basin, or the underlying mantle may have contained enough heat and partial melt to force material upward. No single condition necessarily explains every patch. That is what makes the exceptions more informative than a perfectly uniform absence would have been. The far side did possess volcanic pathways, but they were difficult to create and apparently difficult to maintain. Its rare maria are therefore not failed copies of the near side's Great Plains. They are geological experiments preserved in separate craters, each marking a place where the hidden interior briefly overcame the thick barriers above it, before the pathway cooled and closed again. A dark lava floor lies inside the enormous Tsiolkovsky crater. Tsiolkovsky contains one of the far side's most striking geological contradictions. A towering mountain rises from the center of a floor that was later drowned in dark lava. The crater is about 185 kilometers wide, large enough for the impact that formed it to create terraced walls, a scalloped rim, and a central peak rising roughly 3.4 kilometers above the surrounding floor. That mountain formed during the impact itself, when immense pressure made the underlying rock behave temporarily like a deformable material. As the crushed ground rebounded and the crater walls collapsed inward, deeply buried rock was pushed upward within seconds, leaving a peak where the lowest part of the new cavity might otherwise have remained. The volcanic floor belongs to a later chapter. After the crater had formed and settled, basaltic magma found a route through fractures beneath it and spread across portions of the interior. The liquid rock pooled in the lower ground, cooled into a smooth plain, and surrounded the central peak without covering it completely. Because basalt reflects less sunlight than the surrounding highland material, the floor appears dark while the peak remains bright, allowing the sequence of events to be read almost at a glance. Impact first, uplift next, eruption later. The lava did not create the crater, and the central mountain is not a volcano. They are products of entirely different processes preserved inside the same boundary. Scientists are especially interested in the contact zones where dark basalt meets lighter wall and peak material, because these borders may reveal the thickness of the lava, the composition of the older crust, and the order in which landslides, impacts, and eruptions modified the interior. Tsiolkovsky also demonstrates how a giant crater could provide magma with access through an otherwise resistant far-side crust. Its impact may have fractured the shell deeply enough to create pathways that remained useful long after the original violence ended. The dark floor is therefore the result of destruction followed by delayed renewal, an ancient wound that later became a basin for molten rock, preserving two radically different moments of lunar history within one enormous circle. Why Tsiolkovsky looks like a black eye on the moon's hidden face. From orbit, Tsiolkovsky does not resemble an ordinary crater so much as an enormous dark eye opened in the wrong place. The effect is created by contrast rather than true blackness. Much of the crater floor is covered by basalt, a volcanic rock containing dark minerals that reflect less sunlight than the pale crustal terrain surrounding it. Beside the brighter highlands of the far side, this smooth, low reflectance floor appears almost ink dark, especially in wide images where the finer details disappear and only large patterns remain. Rising from near the middle is a much brighter central mountain, while portions of the elevated rim form a lighter boundary around the dark interior. Your mind instinctively turns this arrangement into something familiar, a dark iris enclosed by a pale outline, with the central peak resembling a reflection or pupil. This tendency to recognize faces and eyes in natural shapes is called pareidolia, but the visual illusion rests on real geological differences. The basaltic floor and the brighter mountain do not merely occupy different elevations. They are made of materials that interact with light differently. When the sun stands relatively high above the crater, shadows shorten and the contrast in surface reflectivity becomes especially clear, allowing the dark volcanic floor to dominate the view. Under lower illumination, long shadows from the walls and peak complicate the shape, making the crater appear deeper, harsher, and less symmetrical. The feature also stands out because most of the surrounding hemisphere lacks similarly broad dark areas. A patch that might blend into the volcanic landscapes of the near side becomes visually dramatic when placed inside the far side's brighter terrain. Photographs taken during the Apollo era helped make Tsiolkovsky one of the hidden hemisphere's most recognizable landmarks, even though no observer on Earth can look directly at it through a telescope. The black eye is therefore not evidence of a strange substance, an artificial mark, or a permanently shadowed hole. It is a lesson in how mineral composition, landscape structure, illumination, and human perception can combine to give lifeless geology an almost living expression. Nothing there is watching you, yet once your brain has recognized the eye, it becomes difficult to see the crater as anything else. Mare Moscoviense is one of the few lunar seas hidden from Earth. Near the northern reaches of the far side lies a dark plain whose name suggests an ocean. Although no liquid water has ever filled it, Mare Moscoviense, the Sea of Moscow, is one of the few large volcanic regions completely concealed from observers on Earth, and its existence immediately complicates any simple claim that the hidden hemisphere never experienced major eruptions. It occupies part of the Moscoviense impact basin, rather than covering the entire depression, creating a dark interior surrounded by elevated, brighter terrain. Measurements from the Lunar Reconnaissance Orbiter reveal how dramatic this setting really is. The lowest ground within the wider basin region falls more than 5 kilometers below the Moon's average reference level, while the highest parts of the rim rise about 6 kilometers above it, producing a total relief greater than 11 kilometers. That vertical range is larger than the difference between many of Earth's mountain summits and deep ocean floors. Yet without air, clouds, vegetation or water, the scale is difficult to judge from photographs. Mare Moscoviense is also not the product of one eruption spreading outward in a single event. Geological mapping and crater counting studies indicate that its visible basalt is divided into several units with different compositions and ages. Some deposits appear to have formed roughly 3.5 billion years ago, while younger eastern flows may be closer to 2.5 or 2.6 billion years old. This means volcanic activity returned to the basin after an interval approaching 1 billion years, using pathways that either reopened or were replaced by new fractures. The separate flows also suggest that magma did not always rise from exactly the same source, or carry the same mixture of minerals. The mare's boundaries contain places where dark basalt meets ancient highland rock over very short distances, making the region especially valuable for any future mission capable of collecting samples from both materials. Such samples could compare the volcanic interior of the far side with the crust that enclosed it, revealing how magma traveled through an environment generally resistant to eruption. Mare Moscoviense may look like a simple dark stain in a global image, but closer examination transforms it into a layered record of repeated volcanic episodes, deep topography, and long pauses during which the moon appeared quiet before molten rock returned. Its ancient name calls it a sea, yet what it truly preserves is not water, but the memory of an interior that awakened more than once beneath a hemisphere we once assumed was almost entirely dormant. Scientists still do not fully understand why lava broke through in only a few far-side regions. The most puzzling evidence of far-side volcanism may be the magma that never reached the surface. Orbital images show only the eruptions that succeeded, but molten rock could have formed beneath many other regions, risen part-way through the crust, and then stopped underground without leaving a visible lava plain. This distinction matters because producing magma and erupting magma are separate challenges. First, part of the mantle must melt. Then the liquid must gather into a volume large enough to move, become buoyant relative to the surrounding rock, enter a fracture, and maintain enough pressure to force that fracture upward. As magma climbs, it can cool, crystallize, lose pressure, or reach a level where its density is nearly equal to the material around it. At that point, it may spread sideways and harden as an underground intrusion rather than erupting. The far side may therefore contain hidden sheets and chambers of volcanic rock beneath terrain that appears completely non-volcanic from above. Impact basins can improve magma's chances by removing overlying material, disturbing the local stress field, and producing deep zones of weakness. But even a large basin does not guarantee an eruption. The orientation of fractures matters, as does the depth at which melting occurs, the chemical composition of the liquid, and the weight of the crust pressing down upon it. Recent studies have challenged the idea that crustal thickness alone can explain the uneven distribution of lunar lava. A thick shell generally makes ascent more difficult, yet some far-side basins contain volcanic deposits, while other regions with relatively thin crust remain surprisingly free of broad lava plains. This suggests that different controls operated together and that their importance changed from one location to another. In one basin, an impact-created fault may have connected a magma source to the surface. Elsewhere, melt may have lacked sufficient buoyancy, become trapped beneath the crust, or arrived after the fractures had already cooled and sealed. Scientists are trying to reconstruct these invisible failures using gravity measurements, spectral maps, surface ages, and models of how magma moves through fractured rock. But direct samples and seismic observations remain limited. The few successful far-side eruptions are therefore like surviving doors in a building whose other entrances have been buried inside the walls. They show that passage was possible without revealing why it opened only there. Understanding those rare breakthroughs may eventually teach us that the far side's volcanic history was not simply a story of missing magma, but of magma repeatedly rising toward the surface and losing its struggle within the final kilometers. The hidden side's thick crust may have trapped most of its magma underground. Vast amount of far-side volcanism may be invisible because its magma rose through the moon and failed only a few kilometers before reaching open space. Forming molten rock deep underground is merely the beginning of an eruption. The magma must also separate from its source, gather into cracks, and push upward through a crust that resists being split apart. Across much of the hidden hemisphere, that journey was unusually long because the outer rocky shell grew much thicker than it did on the side facing Earth. As magma entered a fracture, its pressure had to remain strong enough to keep the crack open while the surrounding walls squeezed inward. Every additional kilometer gave the liquid more time to lose heat, grow crystals, and become less mobile. Some magma may have stopped at a level where it was no longer buoyant enough to rise, spreading sideways between rock layers as a sheet called a sill. Other bodies may have solidified inside steep fractures, known as dikes, or gathered into larger underground intrusions, leaving no dark flow visible at the surface. This possibility changes how you interpret the far side's apparent volcanic silence. A landscape without extensive lava does not necessarily indicate an interior that never melted. It may instead conceal a buried architecture of frozen magma, preserved beneath highlands that look entirely untouched from above. Research on returned Chang'e 6 basalt has strengthened the argument that far-side mantle material was not universally incapable of producing magma. Some studies suggest that the great difference in surface volcanism may have depended heavily on whether molten rock could penetrate the thicker shell. Large impacts sometimes created temporary weaknesses, but most fractures may not have remained open long enough to complete the ascent. Future seismic networks and more detailed gravity measurements could reveal dense underground bodies left by these failed eruptions. Until then, the bright far-side surface may be hiding a darker history beneath it. What appears to be a hemisphere where volcanism rarely happened could instead be a world where volcanism repeatedly began, climbed through ancient rock, and quietly froze before it ever saw the sky. Heat-producing elements are far less common across much of the far side. The far side may have grown geologically quiet sooner, because much of it was born with fewer natural heaters buried inside its rocks. Potassium, thorium, and uranium contain long-lived radioactive forms that release small amounts of energy as their atoms slowly change over immense periods. A single grain produces almost nothing you could feel, but distributed through a planetary interior. These elements can influence how quickly rock loses heat and how long portions of the mantle remain capable of melting. Scientists learned that they are unevenly distributed across the Moon by using orbital instruments that detect gamma rays and other particles produced at or near the surface. Thorium is especially useful because its signal can be mapped from orbit and often points toward material enriched in other heat-producing elements. Those maps reveal broad expanses of the far side with very low concentrations compared with the strongest near-side regions. The pattern probably began during the cooling of the Moon's early molten interior. Many common minerals incorporated only small amounts of these elements as they crystallized, so potassium, thorium, and uranium tended to remain in the final portions of liquid. Where that last material eventually collected became important for the Moon's later thermal evolution. Regions that received little of it would have lost their original heat without much long-term replacement, allowing the mantle below to cool, strengthen, and resist further melting. Yet the far side is not chemically empty. Small enriched areas exist, including unusual thorium signatures near Van de Graaff crater, showing that the ancient redistribution was complicated rather than perfectly divided. Impacts may have excavated enriched layers, moved debris across the surface, or exposed rare pockets that form beneath otherwise depleted terrain. This means orbital maps must be read as records of both original composition and later disturbance. Still, the global contrast is difficult to ignore. The far side's colder geological character may be the result of a quiet deficiency established billions of years ago. Fewer unstable atoms, less heat released through time, and a shorter window in which the interior could continue reshaping the surface. The fate of a hemisphere may therefore have depended partly on elements so scarce that you could walk across the landscape without ever knowing they were missing. The near side contains a radioactive chemical province, almost missing from the hidden hemisphere. One enormous region on the near side contains a chemical concentration so unusual that it has been classified almost like a separate geological country. Scientists call it the Procellarum Creep Terrain, a province centered broadly around Oceanus Procellarum and the Imbrium region. The name Creep combines the letter used for potassium with abbreviations for rare earth elements and phosphorus. But the material also tends to contain elevated thorium, uranium, and other elements that did not easily enter the common minerals, crystallizing from the Moon's early magma. They became concentrated in the final leftovers of that ancient liquid, like ingredients remaining in a shrinking pool after most of the surrounding material had already solidified. On the near side, those leftovers accumulated on a remarkable scale. Orbital maps show a broad, thorium-rich zone associated with chemically distinctive crust and many of the Moon's great volcanic landscapes. Because potassium, uranium, and thorium release heat through radioactive decay, their presence may have helped this province remain warmer than much of the rest of the Moon. Creep-rich material may also have affected how nearby mantle rocks melted, allowing volcanic activity to continue or return after other regions had cooled. Yet scientists still debate why this chemical reservoir became concentrated so strongly in one hemisphere. It may have gathered unevenly during the final crystallization of the lunar magma ocean, been moved by slow overturn inside the mantle, or been redistributed when the enormous Imbrium impact disturbed the crust and interior. More than one of these processes may have contributed. What makes the province especially mysterious is how weakly it is represented across most of the far side. There are isolated, enriched locations beyond the main terrain, but nothing there matches the size and intensity of the near-side concentration. This imbalance suggests that the Moon did not merely develop different surfaces. It separated some of its most influential chemical ingredients into one dominant region. The dark plains you see from Earth may therefore be connected to an invisible reservoir beneath them, a province where rare elements prolonged heat and encouraged geological change. What looks like a familiar face in the night sky may actually be the outward expression of the Moon's most chemically exceptional interior, while the hidden hemisphere preserves what the world became without receiving the same buried inheritance. This chemical imbalance may explain why one side was covered in lava and the other was not. The great volcanic divide across the Moon may have begun with a small group of elements that refused to fit neatly into the minerals forming around them. As the early lunar interior crystallized, potassium, rare earth elements, phosphorus, thorium, and uranium tended to remain within the last portions of melt, rather than entering the most common solid crystals. This leftover material did more than preserve an unusual chemical signature. Some of its elements released heat slowly through radioactive decay, while others changed the melting behavior of the surrounding mantle. Where this material became concentrated beneath the near side, it may have created a long-lived thermal and chemical advantage. The mantle did not need to become completely molten. Even a modest reduction in the temperature required for partial melting could generate pockets of magma, and continued internal heating could replace some of the energy escaping into space. Recent research also points to the possible importance of titanium-rich minerals in near-side mantle material. When dense, titanium-bearing cumulates sank after the lunar magma ocean crystallized, they may have mixed with deeper rock and made some regions easier to melt. This would help explain not merely why lava existed, but why volcanic activity could continue across such an extended period and produce flows with different compositions. The far side, lacking the same broad chemical reservoir, may have crossed the threshold for melting less frequently and in fewer places. Its mantle could still produce magma, as returned far side basalts now confirm, but the process appears to have been more limited and less persistent. Chemical enrichment was therefore not an underground switch that turned one hemisphere on and the other off. Crustal structure, impacts, pressure, and mantle circulation still influenced where eruptions succeeded. Yet chemistry may have loaded the odds from the beginning, giving one side more internal heat, more melt-friendly material, and more time to send magma upward. When you compare the Moon's dark familiar plains with the pale hidden hemisphere, you may be seeing the surface consequences of ingredients sorted billions of years earlier, when a slight chemical imbalance deep inside a cooling world slowly grew into one of the most visible divisions in the solar system. The young Earth may have heated one side of the newborn Moon more than the other. Imagine a time when Earth was not the cool blue sphere you recognize, but a vast incandescent world radiating enough heat to influence the surface of its newly formed companion. After the giant collision thought to have produced the Moon, Earth's outer layers would have been extremely hot, possibly containing a deep magma ocean beneath a glowing atmosphere of vaporized rock. The young moon also orbited much closer than it does today, making Earth appear enormously larger in its sky. If the moon became tidally locked early, one hemisphere would have remained turned toward this radiant planet, while the opposite hemisphere faced mostly cold space. Both sides still received sunlight, but only the near side received the additional infrared energy pouring from the post-impact Earth. This would not have roasted one hemisphere while leaving the other frozen. The proposed temperature difference was subtler, yet during the delicate period when molten rock was cooling and the first crust was beginning to assemble, even a moderate imbalance could matter. The Earth-facing surface may have lost heat more slowly, delaying the condensation and solidification of some materials, while the far side cooled more efficiently by radiating energy into space. Tides may have strengthened the asymmetry in a different way. Because the early moon was close and its orbit was not perfectly circular, Earth's gravity repeatedly flexed the lunar interior, producing frictional heat that some models suggest could have been greater on the near side. Several heating processes may therefore have worked together rather than one acting alone. The hypothesis remains unproven because no instrument can return to watch the first few million years of lunar history, and later impacts have heavily altered the evidence. Scientists must instead compare crustal thickness, mineral ages, chemical patterns, and computer models to determine whether the required temperature contrast was realistic and long-lasting. Still, the possibility changes the way you picture the early Earth-Moon system. Earth may not have been a distant object that merely held the moon in orbit. It may have acted like a furnace hanging almost motionless over one hemisphere, quietly influencing how quickly the newborn world cooled. The moon's permanent orientation could then have carried a geological consequence. The side that looked toward Earth inherited its warmth, while the side facing outward began hardening beneath the deeper cold of space. Earth's glow could have helped create the moon's two completely different faces. Before Earthshine became the gentle reflection that illuminates the dark portion of a crescent. Moon today, it may have been powerful enough to rearrange the materials from which the first lunar surface was built. In the Earthshine hypothesis, the hot young Earth created a persistent temperature gradient across the nearby, synchronously rotating moon. The crucial effect was not simply that one side stayed warmer. Different temperatures could have changed where vaporized substances condensed, where crystals formed most efficiently, and how material circulated through the moon's early atmosphere and magma ocean. Refractory compounds containing aluminium and calcium are important because they contributed to plagioclase, the light mineral that helped form the ancient highland crust. On the cooler far side, these substances may have condensed sooner or accumulated more effectively, allowing greater quantities of buoyant crust-forming crystals to gather there. Meanwhile, the warmer near side may have remained molten or partially molten for longer, delaying the construction of an equally thick surface layer. A newer version of this idea proposes that the temperature difference could also have driven large-scale circulation within the lunar magma ocean. Shallow molten material and floating crystals might have been transported toward the cooler hemisphere, while deeper return flows moved in the opposite direction. If such circulation persisted, a modest initial thermal contrast could have become a substantial structural difference, leaving extra crust on the far side and a thinner shell on the side facing Earth. That thinner region would later have been easier for impacts and internal activity to modify, gradually producing the two landscapes seen today. Yet this remains a developing hypothesis, not a settled account. Alternative models invoke mantle overturn, enormous impacts, uneven tidal heating, or even the accretion of a smaller companion moon. Recent analysis of Chang'e 6 anorthosite fragments also suggests that primary crust formation may have been broadly comparable across both hemispheres, which could mean the strongest differences emerged through later reworking rather than during the earliest solidification alone. Earthshine may therefore have planted the first imbalance without creating the finished faces by itself. The idea is compelling because it turns light into a geological force. Radiation from one young world may have guided minerals across another, allowing the moon's orientation toward Earth to become written permanently into its crust. When you see its mismatched hemispheres now, you may be looking at the distant consequence of a time when Earth did not merely shine upon the moon, but helped decide what kind of surface each side would become. Another theory suggests a smaller moon once collided with the far side. The most unexpected explanation for the moon's uneven shape begins with the possibility that Earth once had not one moon, but two. According to this hypothesis, the giant collision that created the disk of debris around the young Earth may have produced several lunar bodies rather than assembling everything immediately into a single object. Most would have collided, escaped, or been absorbed quickly, but computer models suggest that one smaller companion, perhaps around 1,200 kilometers across, could have survived for tens of millions of years near a gravitationally balanced region of the Earth-Moon system. It would have formed from material similar to that of the larger moon, yet its smaller size would have allowed it to lose heat and solidify more rapidly. While the main moon still retained a deep, molten interior, the companion may already have developed a thick crust and a mostly solid mantle, possibly with little or no metallic core. Its survival would not have been permanent. As the moon's orbit slowly changed and gravitational disturbances accumulated, the smaller body could have left its protected position and entered a collision course with the larger moon. This proposal is known informally as the companion moon or Big Splat hypothesis, but it must not be mistaken for a discovered chapter of lunar history. No intact second moon has been found, and there is no single rock that can yet be identified as a surviving piece of it. The idea comes from simulations showing that multiple moons can emerge from a debris disk and that a late merger could reproduce some features of the far side. It is attractive because it connects two mysteries: why a smaller satellite might naturally form beside the moon, and why so much extra material appears to exist across one hemisphere. Yet attraction is not proof. The model depends on the companion surviving long enough, entering the correct orbit, and striking at an unusually gentle speed and favorable angle. You are therefore not being asked to picture a hidden moon with certainty, but to consider a scientifically testable possibility. Perhaps the far side's highlands are not made entirely from the moon that survived, but partly from a lost sibling, whose final orbit ended by becoming part of the world beside it. A slow ancient collision may have piled extra crust onto the hidden hemisphere. A collision between worlds does not always excavate a circular hole. Under the right conditions, one body can be spread across another like an immense geological layer. In the companion moon simulations, the smaller object would have approached at roughly 2 to 3 kilometers per second, slow by the standards of planetary impacts and below the speed at which shock waves travel through common silicate rock. That distinction changes the outcome. A much faster collision would compress, melt, vaporize, and eject enormous quantities of material, leaving a deep basin surrounded by widely scattered debris. A slower merger would still be catastrophic on any human scale, but much less explosive relative to the size of the bodies involved. The smaller moon would be crushed and flattened as it struck, with much of its rocky exterior remaining on the larger moon instead of being launched back into space. Simulations show its material spreading across a broad hemisphere as an accretionary pile, adding a layer tens of kilometers thick in some regions and raising the average elevation of the land beneath it. The collision would not leave a neat boundary where one moon ended and the other began. Pressure, friction, landslides, and later impacts would mix the incoming rocks with the original crust until the added body became almost impossible to recognize as a separate object. The model also predicts that the force of the merger could push deeper, chemically evolved material away from the impact hemisphere and toward the opposite side, potentially linking far side thickening with the near side's unusual chemical concentration. Yet the details are demanding. The impact must be slow enough to deposit material rather than excavate it, large enough to affect nearly an entire hemisphere, and timed after much of the main moon's outer region had solidified. A different speed, size, or angle could produce an ordinary giant basin, destroy too much crust, or distribute the debris incorrectly. This is why the hypothesis remains compelling but unconfirmed. It offers a physical mechanism that can build mountains by addition rather than uplift, transforming a second moon into a permanent outer layer. If it happened, the far side's extra crust would not have risen entirely from the moon's interior. Some of it would have arrived from the sky during a collision so slow that the smaller world was not blasted away, but pressed into the larger one, until two separate histories became a single surface. Scientists cannot yet agree on which theory best explains the far side's thickness. The debate survives because every proposed explanation solves part of the mystery while leaving another part untouched. The companion moon model can add a broad layer of crust to one hemisphere, but it requires a second body with a particular size, orbit, speed, and impact geometry that have not been independently demonstrated. Earthshine models can create an early temperature contrast and redirect crust-forming material toward the cooler far side. Yet researchers must still determine whether that contrast lasted long enough and moved enough material to produce the thickness now measured. Uneven tidal heating could have warmed the near side more strongly, but heating alone does not automatically reproduce the moon's full pattern of elevation, chemistry, and volcanic history. Other simulations propose that a giant impact struck the present near side, excavating a vast low region while depositing deeper material elsewhere. A separate family of models gives the South Pole Aitken impact a central role, suggesting that its immense heat disturbed mantle circulation and helped move dense, chemically unusual material toward the near side. Each theory can be adjusted to match selected observations, but the moon preserves several constraints at once: the shape of its gravity field, the thickness and density of its crust, the distribution of minerals, the ages of its rocks, and the locations of ancient basins. A successful explanation must reproduce all of them in the correct sequence. Gravity missions such as Grail revealed where the crust is thick and thin, but gravity cannot directly tell scientists when the contrast developed or which event caused it. Return samples provide ages and compositions, yet until recently nearly all came from the near side. Chang'e 6 has begun changing that imbalance. A 2026 study of far-side anorthosite fragments found that their primary crustal material is broadly comparable to Apollo anorthosites, supporting the possibility that both hemispheres first developed from a similar global magma ocean, and that the strongest contrast arose through later reworking. This result narrows the possibilities, but it does not identify one winner. A companion moon collision, giant impacts, mantle movement, and asymmetric heating could all occur after or during different stages of crust formation, and more than one process may have contributed. The disagreement is therefore not a sign that lunar science has failed. It reflects the difficulty of reconstructing a chain of events more than 4 billion years old from rocks that have been melted, fractured, buried, and moved repeatedly. The moon may not offer one dramatic answer, because its two faces may have emerged through several causes acting one after another. To solve the mystery, scientists will need samples from additional far-side highlands, seismic measurements of the deep crust, and models tested against the same complete set of evidence. Until then, the thick hidden hemisphere remains less like a single clue awaiting recognition and more like a final result produced by a history whose steps have not yet been placed in the correct order. The far side contains giant basins buried beneath billions of years of later impacts. Some of the largest structures on the moon are no longer visible as obvious craters, because the far side has spent billions of years writing newer destruction over older destruction. When an immense early collision created a basin, it produced a broad depression surrounded by rings of fractured and uplifted crust. At first, those rings may have stretched clearly across hundreds of kilometers, but the landscape did not remain untouched after the basin formed. Later asteroids opened new craters through its rim, scattered ejecta across its floor, buried sections beneath thick blankets of broken rock. and sometimes created additional basins whose deposits crossed the earlier structure. After enough overlapping events, the original outline became fragmented into isolated ridges, curved valleys, changes in slope, and subtle arcs that no longer looked connected to the eye. Scientists now recover these lost shapes by combining several kinds of evidence. Elevation maps can reveal a shallow circular depression, even when photographs show only chaotic terrain. Gravity measurements can expose a buried arrangement of dense and light material created when the basin formed. Geological maps trace old faults, scarps, and rock units that curve around a common center, while crater relationships show which features cut across others and must therefore be younger. In some cases, a basin that appears almost absent in ordinary images becomes unmistakable when its topography and gravity are viewed together. This has led researchers to identify more large lunar basins than older photographic surveys could recognize, including structures whose rings were hidden beneath later damage. Yet calling them buried does not always mean they lie beneath one continuous layer like ruins under soil. Many survive as incomplete geological patterns dispersed across the surface, with one part covered, another eroded by impacts, and another preserved as a distant rise. The far side is therefore not a clean museum of ancient craters. It is a reused surface where every new collision borrowed material from what came before and rearranged the evidence. When scientists reconstruct one of these giant hidden basins, they are doing something close to reading a sentence after most of its letters have been overwritten. The message is incomplete, but the curve of the remaining marks still reveals that an enormous event once crossed the page. Some hidden craters are so old that newer craters have almost erased their original shape. Age on the Moon does not always make a crater deeper and more impressive. Given enough time, it can reduce a once dramatic structure to a faint suggestion of a circle. A fresh crater normally has a sharp rim, steep inner walls, a clearly defined floor, and ejecta that spreads outward in recognizable patterns. An extremely old crater may retain almost none of these features. Repeated small impacts slowly chip away at the rim and fill the interior with loose debris, while larger collisions can remove entire sections of the wall in a single event. Material ejected from distant craters falls across the landscape and gathers inside older depressions, gradually raising their floors and softening the difference between the inside and outside. Powerful nearby impacts may also send seismic vibrations through the Moon, causing unstable slopes to collapse and loose material to slide downward. Because the far side highlands are already densely cratered, many ancient rims have younger craters sitting directly on top of them, sometimes arranged so closely that the first structure becomes difficult to separate from the damage that followed. Eventually, the terrain approaches crater saturation, a state in which new impacts destroy old features almost as quickly as they create new ones. The surface continues recording collisions, but it can no longer preserve every record clearly. Scientists identify these degraded craters by searching for interrupted arcs, low rounded ridges, shallow bowl-shaped changes in elevation, and patterns of younger craters that appear to lie within a larger vanished boundary. Lighting can dramatically affect whether such a feature is noticed. When the sun is low, a weak rim may cast a long shadow and briefly reveal its curvature. Under overhead illumination, the same crater can disappear into a confusing field of similar brightness. This is why lunar age cannot be judged from darkness or size alone. A nearly invisible crater may be far older and historically more important than a spectacular sharp-edged one nearby. Its faded condition is itself evidence, showing that it has remained exposed through an immense sequence of later events. The oldest scars do not always announce themselves with grandeur. Sometimes they survive only as a slight bend in the ground, asking you to recognize that erasure is also a form of preservation, because the damage that hides the crater simultaneously proves how long it has been there. Hertzsprung Basin is one of the largest impact structures hidden from Earth. Hertzsprung is so wide that a traveler crossing its interior could pass through several younger craters before realizing that all of them lie inside a much greater ancient structure. Located on the lunar far side, the basin spans about 570 kilometers, making it larger than many familiar volcanic plains on the hemisphere visible from Earth. Its scale alone is impressive, but its internal architecture is what makes it especially valuable. Hertzsprung possesses a prominent outer ring and a rugged inner ring roughly 270 kilometers across, with possible fragments of additional rings between and within them. This places it in an important transitional category. It is more structurally complex than a simple two-ring basin, yet not as fully developed as the greatest multi-ring systems. Scientists study this intermediate form because it may reveal how enormous impacts begin transforming an ordinary crater into a landscape of concentric mountain chains. During the collision, the surface would have opened into a temporary cavity too deep and unstable to survive. The floor rebounded, surrounding rock moved inward, and enormous blocks of crust were uplifted into rings as the cavity collapsed. Those rings now expose material from different depths, including bright boulders on the inner ring that have been interpreted as nearly pure anorthosite, a rock associated with the Moon's ancient crust. Hertzsprung is classified as nectarian in age, meaning it formed during a very old period of major basin creation, but its appearance has been heavily modified since then. Younger craters pierce its rings and interior, while debris connected with the later Oriental impact appears to have crossed parts of the basin, complicating attempts to identify which exposed rocks truly belong to Hertzsprung. This contamination is scientifically important rather than merely inconvenient, because it demonstrates how material from one enormous collision can travel into another ancient structure and confuse the geological record. Researchers must therefore distinguish local rock excavated by Hertzsprung from foreign debris deposited much later. From Earth, this vast system remains beyond direct view, but spacecraft mapping has turned it into a natural experiment in the physics of giant impacts. Hertzsprung is not simply one more large circle on a crowded hemisphere. It preserves the moment when a collision became large enough to reorganize the crust into rings, while every younger scar across it reminds you how difficult it is for even a structure hundreds of kilometers wide to remain unchanged by time. The Apollo Basin sits inside an even greater scar on the far side. A crater nearly 500 kilometers wide should dominate any landscape. Yet Apollo Basin is so deeply nested inside a greater wound that it becomes only one chapter within a much larger catastrophe. Apollo lies in the northeastern region of the South Pole Aitken Basin, meaning that the object which created it struck ground already transformed by an earlier collision of almost unimaginable scale. This relationship is known through superposition. Apollo's rim, inner mountain ring, fractured floor, and surrounding deposits were formed after the older basin had lowered, weakened, and chemically altered that part of the lunar crust. Apollo is itself a peak ring basin, a class of impact structure produced when a collision becomes too large to leave behind the simple central mountain seen in smaller complex craters. During its formation, the temporary cavity collapsed so violently that deeply displaced rock rose as a broad ring of mountains within the outer rim. Much of that ring has since been damaged, but broken arcs still trace the structure across the interior. The basin's location inside South Pole Aitken makes its geology unusually difficult to read. A rock exposed within Apollo may belong to the original far side crust, material modified by the South Pole Aitken collision, debris excavated when Apollo formed, or deposits delivered by an even younger impact. The two great events also reached different depths and occurred under different conditions, so their products may be mixed without being identical. This nesting gives scientists a rare opportunity to compare how the Moon responded to enormous collisions at separate moments in its early history. The older event established the regional foundation. The younger one reopened it, rearranged it, and exposed layers that had already survived a planetary scale disaster. Apollo Basin therefore cannot be understood as an isolated hole cut into ordinary ground. It is an impact structure carved into another impact structure, a wound formed inside the altered remains of a previous wound. Seen this way, the lunar surface stops resembling a collection of independent circles and begins to look like a sequence of geological decisions, each collision inheriting the damage left by the one before it. Apollo may be immense, but the landscape containing it reminds you that scale is always relative. What appears large enough to define a world can still exist inside something older, deeper, and far greater. One ancient impact basin can contain dozens of younger craters inside it. An ancient lunar basin can become so crowded with later craters that its floor begins to resemble a separate world rather than the interior of a single impact structure. Once a basin forms, it does not become protected from future collisions. Its enormous floor continues moving through space with the rest of the Moon, receiving impacts from objects of many sizes over billions of years. A small projectile may create a simple bowl only a few kilometers wide, while a larger one can produce terraced walls, landslides, a central mountain, and an ejector field that crosses older features nearby. Given enough time, dozens or even hundreds of these younger structures accumulate within the original boundary. Some sit entirely on the basin floor. Others cut through the inner mountain ring, overlap the outer rim, or straddle the border between the basin and surrounding highlands. This creates a natural hierarchy of events that scientists can read using relative dating. A crater that interrupts another crater's rim must be younger. An ejector blanket lying across an older floor must have arrived later. A small crater partly buried beneath another deposit must already have existed before that material was placed over it. No written date is required for the first stage of this reconstruction. The order is preserved through physical relationships between the structures. The process becomes more complicated when younger impacts excavate older buried material. A new crater may punch through loose debris accumulated on the basin floor and expose rock from the original impact melt beneath it, bringing a much older chapter back to the surface inside a much younger feature. Other impacts scatter fragments across the basin, so material collected from one small crater may have originated far beyond its rim. Eventually, the old basin becomes a container holding many overlapping geological environments: smooth deposits, fractured mountains, buried melt sheets, secondary crater fields, and fresh exposures cut into ancient ground. Its original floor may survive only in disconnected patches between younger scars. This is why a basin's age cannot be understood by choosing one crater inside it and treating that crater as representative of the whole region. Every feature belongs to a different moment, and the landscape is a stack of events disguised as a single view. When you look across such terrain, you are seeing time arranged spatially. The oldest catastrophe defines the enormous boundary, while each younger crater places another clock inside it, until one ancient wound contains a crowded archive of countless later collisions. Enormous collisions. Once covered the hidden side with mountains of flying debris. For a few terrifying minutes after a basin-forming impact, the far side of the Moon would have been hidden beneath an expanding curtain of rock. The incoming body struck at many kilometers per second, compressing the surface so rapidly that the ground could not respond like ordinary solid stone. Rock near the impact point was crushed, shocked, heated, and accelerated outward while the temporary cavity opened below. Vast volumes of crust rose above the surface in a moving ejector curtain, with different fragments following different paths according to their speed and launch angle. Some material traveled only a short distance before falling back near the rim, building a deep, chaotic blanket containing broken blocks, melted fragments, and pulverized stone. Faster debris crossed hundreds of kilometers before returning, spreading thinner deposits across regions far beyond the visible basin. Because the Moon has no thick atmosphere, the fragments were not slowed by air or shaped by wind. They traveled along clean ballistic arcs, temporarily becoming small projectiles orbiting above the landscape before gravity pulled them down again. The largest blocks struck with enough energy to excavate secondary craters, while groups of fragments produced clusters and long chains that still point back toward the original collision. Near the basin, the deposited debris could reach extraordinary thicknesses. Measurements and models of well-preserved lunar basins indicate that proximal ejecta may be measured in kilometers near major outer rings before thinning with distance. This means entire pre-existing landscapes could be buried beneath a new layer of displaced crust, their craters, ridges, and chemical signatures hidden under material imported from elsewhere. The returning ejecta did not settle gently. Dense flows of fragments moved across the ground. Blocks collided, slopes failed, and hot impact melt gathered in low areas between colder debris. Some pieces escaped the moon completely. Others may have entered temporary orbits and returned much later, carrying lunar material to locations unrelated to the original scar. The phrase flying debris can sound like dust scattered from an explosion, but events of this scale moved mountainous quantities of rock and reorganized terrain across a significant fraction of a hemisphere. The far side surface is therefore made partly from ground that did not originate where it now rests. Beneath many craters may lie ejecta from older basins, and beneath that ejecta may lie structures created by still earlier impacts. A colossal collision did not end when the cavity stopped expanding. Its consequences continued wherever the falling debris landed, turning destruction at one location into a new geological layer across an immense surrounding world. Material blasted from one crater can be found hundreds of kilometers away. A rock discovered on the far side may be standing hundreds of kilometers from the place where it was born, carried there during a journey that lasted only minutes. When a large object strikes the moon, the expanding crater launches fragments at many different speeds and angles. Material thrown gently falls close to the rim, where it forms a thick blanket containing shattered crust and impact-melted rock. Faster fragments climb much higher above the surface and travel across vast distances before lunar gravity pulls them down again. With no thick atmosphere to slow them, burn them, or scatter them through turbulent air, these pieces follow long curved paths through empty space. Some land almost intact, but many strike hard enough to open secondary craters and mix themselves with material excavated from the new landing site. This mixing creates a scientific challenge. A distant ray extending from a young crater may contain only a small fraction of rock from the original impact site, because each returning fragment digs up a much larger quantity of local ground and blends the two together. Researchers therefore cannot assume that every bright particle found along a ray came directly from the parent crater. They examine mineral composition, spectral signatures, crater patterns, and the direction of the deposits to estimate how far the foreign material traveled and how heavily it was diluted. This process also means that a single collision can distribute geological information across an enormous region. Material excavated from beneath one crater may arrive on an older plain, cross a basin boundary, or fall into another crater that formed billions of years earlier. Later impacts can lift those fragments again, sending them on a second journey and making their final location even more misleading. Lunar meteorites found on Earth show that impact debris can sometimes travel much farther still, escaping the moon completely before eventually reaching another world. The far side is therefore not arranged like a library in which every stone remains on its original shelf. It is more like a collection whose pages have been torn out, thrown across the room, and inserted into different books. To read one fragment correctly, scientists must reconstruct its path backward through the violence that moved it. A stone beneath your feet may describe the place where you found it, but it may also be carrying the chemistry of a distant crater hidden beyond the horizon, reminding you that on the moon, location does not always reveal origin. Long crater chains may mark where broken impact debris struck the surface in sequence. Some lines carved across the moon are not valleys or cracks, but the footprints of several falling rocks arriving one after another. When a large impact throws blocks away from its center, the ejecta does not always travel as isolated pieces evenly spread across the sky. Fragments can leave the crater in groups, collide during flight, or break apart under the forces of launch. Because neighboring pieces begin with similar speeds and directions, they return to the surface along related paths. The first fragment creates a crater, the next lands nearby, and others continue the sequence, leaving a chain of depressions that may stretch for many kilometers. These secondary crater chains often appear irregular compared with craters formed by independent asteroids. Their members can overlap, share walls, vary suddenly in size, or form shallow elongated shapes because the fragments strike at low angles. Some chains are accompanied by clusters and herringbone-like ejecta patterns, whose open ends point approximately toward the larger parent crater. By tracing those orientations, scientists can sometimes identify the distant impact that launched the debris, even when the source lies far outside the photographed area. This makes crater chains more than unusual surface markings. They preserve the direction of an ancient explosion and help researchers map how energy and material spread across the moon. Yet not every chain has the same origin. A comet or asteroid can be pulled apart before impact, allowing a train of separate bodies to strike in succession without being launched from another lunar crater. Volcanic collapse pits and certain surface depressions can also resemble impact chains from a distance. Researchers distinguish among these possibilities by examining whether the pits contain raised rims, ejecta, elongated shapes, consistent spacing, and a directional relationship with a known primary crater. Secondary chains are especially important when estimating the age of a surface. If every small crater were counted as an unrelated impact from space, a region covered by secondaries from one event could appear much older than it truly is. One primary collision can generate hundreds, thousands, or even tens of thousands of smaller scars, turning a brief episode into what looks like a long history of bombardment. The chain across the ground is therefore both a record and a warning. It shows how fragments moved in sequence, but it also reminds you that many circles do not necessarily represent many separate moments. Sometimes an entire line of craters is the scattered continuation of one distant impact, written across the surface, like the fading steps of a single event. Some far-side craters contain central mountains, formed in only minutes. A mountain rising from the middle of a lunar crater may look ancient and immovable, yet it can be created almost as quickly as the crater surrounding it. Central peaks appear in complex craters, which form when an impact is powerful enough to excavate a temporary cavity too deep and unstable to preserve its original shape. In the first moments after contact, shock waves compress and fracture the crust, while enormous quantities of rock are driven outward. Once the pressure begins to release, the deeply displaced material beneath the center rebounds upward. For a brief period, the shattered rock behaves less like a rigid floor and more like a dense fluid responding to gravity and pressure. The rising mass can overshoot its stable position, forming a towering peak before part of it collapses and settles into the mountain that remains. At the same time, the steep outer walls slump inward along great faults, widening the crater and building terraces around its edge. The entire transformation from temporary cavity to central mountain can occur within minutes, even though the final feature may survive for billions of years. This is not volcanic construction. No slow accumulation of erupted lava is needed, and the mountain is not a dormant cone with a magma chamber beneath it. It is crust that was pushed downward and then lifted back toward the surface during the impact's rapid collapse. Because the rebound can raise material from several kilometers below the original ground, central peaks offer scientists access to rocks that would otherwise remain buried. Orbital spectrometers sometimes detect minerals on these mountains that differ from those covering the surrounding floor, allowing researchers to investigate the composition of the lower crust without drilling. The height, shape, and mineralogy of a peak can also reveal how the target rock responded to extreme pressure and how deeply the collision disturbed the moon. Not every large crater produces one simple mountain. As impact size increases, the central uplift can become a cluster of peaks, and in still greater structures, it may collapse outward into a broad peak ring. These changing forms show that crater architecture is governed not only by the incoming object, but by the moon's gravity and the temporary movement of its own crust. A central mountain therefore preserves a paradox of geological time. It was assembled with astonishing speed, yet it has remained standing through an age longer than almost any mountain on Earth. What looks like a monument, slowly built by the moon, is actually the frozen crest of a rebound that began almost the instant the surface was destroyed. The moon's crust rebounded like a liquid after its largest impacts. Solid rock seems incapable of flowing until an impact delivers more energy in seconds than the crust can respond to in its ordinary rigid state. During the moon's largest collisions, the incoming object compressed the ground so violently that shock waves shattered mineral structures, opened countless fractures, and briefly weakened an enormous volume of crust. The rock did not literally become an ocean of liquid, and much of it never fully melted, but for a short interval it could move collectively in a fluid-like way. Scientists still investigate the exact mechanism behind this temporary weakness. Extreme pressure, intense heat, pervasive fragmentation, and rapidly traveling vibrations may all have reduced friction between broken blocks, allowing material that normally supports mountains to collapse and flow. One proposed process, sometimes called acoustic fluidization, suggests that powerful vibrations helped separated fragments move past one another more easily, although it remains a model rather than a directly observed event on the moon. Whatever combination occurred, the first cavity produced by a giant impact was far too deep and steep to remain stable. Once the initial downward pressure began to fade, compressed material beneath the center moved upward, while enormous sections of the surrounding crust slid inward under gravity. At basin scale, this motion involved far more than a single central uplift. Deep layers rose, upper layers stretched and fractured, and broad zones of crust shifted horizontally as the temporary cavity transformed into a much shallower final structure. Some numerical models suggest that portions of the mantle may also have risen beneath the largest basins. As overlying crust was removed and redistributed, the entire reorganization happened rapidly, perhaps over minutes to hours, depending on the size of the event. Yet it established structures that survived for billions of years. This is why an impact basin cannot be understood as a hole simply punched into unmoving ground. Its present floor, rings, faults, and buried layers are the result of a world attempting to regain balance after being pushed far beyond the strength of ordinary stone. You are seeing the final still frame of motion so extreme that the moon's crust temporarily lost the behavior you associate with rock. The lesson is subtle but unsettling. Solidity is not an absolute property. Under sufficient pressure, even the foundation of a world can fold, surge, and rebound before becoming rigid again, leaving permanent mountains and depressions as evidence of a brief moment when stone moved, almost like water. Multi-ring basins reveal how the lunar surface responded to planet-sized violence. Concentric mountain ranges hundreds of kilometers apart are the moon's way of showing that some impacts disturbed far more than the place where the projectile first touched the ground. Multi-ring basins are the largest and most structurally complicated impact features, surrounded not by one simple rim, but by several vast rings of ridges, scarps, and faults arranged around a common center. Orientale, located near the moon's western limb, is one of the clearest examples, with enormous circles of mountains that allow scientists to study a relatively well-preserved basin system. It may be tempting to imagine these rings as ripples that froze while spreading across the surface, but that picture is incomplete. The rings are physical structures created as the crust failed at different distances and depths during the collapse of the temporary impact cavity. After the collision removed and displaced an immense quantity of material, the remaining ground could no longer support its former shape. Blocks of crust moved inward, deep faults opened, and sections of rock were pushed upward into curved mountain belts. The innermost rings may have developed when an enormous central uplift became too wide and unstable to remain standing, collapsing outward into a circular chain, rather than surviving as one peak. Outer rings formed through large-scale faulting and the inward movement of crust surrounding the basin. Gravity data have helped scientists look beneath these visible mountains, revealing severe crustal thinning and structural changes extending toward the mantle. The spacing and number of rings vary because each event depended on impact energy, crustal thickness, underground layering, and the thermal condition of the moon at the time. Older basins are harder to interpret because later collisions have broken or buried their rings, leaving only disconnected arcs that must be reconstructed through topography and gravity. Even the best preserved examples continue to generate debate, since different models disagree about which rings mark the edge of the first cavity and which emerged during later collapse. Yet their broader message is clear. A basin-forming impact did not only excavate material, it reorganized a planetary shell across an area comparable to a continent. The rings reveal where the moon bent, broke, and settled into a new configuration after violence reached deep enough to challenge the architecture of the crust itself. When you trace those circles from orbit, you are not following decorative lines around a crater. You are reading the boundaries of structural failure, each ring marking another distance at which the surface could no longer remain what it had been before the impact arrived. The hidden side may contain ancient impact, melt that has remained frozen for billions of years. Beneath some quiet far-side plains may lie lakes of stone that were created in an instant and have remained solid ever since. When a large object struck the moon, part of its energy was converted into heat intense enough to melt both the projectile and substantial volumes of lunar rock. This material was not volcanic magma rising slowly from the mantle. It was impact melt produced near the surface by shock, friction, and extreme compression, often containing ingredients from several crustal depths mixed together within the same temporary liquid. Some melt was thrown outward as droplets, glassy fragments, and coatings on ejecta. Larger quantities flowed downhill across crater floors, gathered in depressions, filled cracks, and sometimes formed broad ponds or sheets beneath a surface of cooling debris. As heat escaped into the airless lunar environment and surrounding rock, these pools crystallized into solid deposits. Small melt bodies may have cooled rapidly into glass, while thick basin-scale sheets could have remained hot for much longer, allowing crystals to grow, dense minerals to sink, and chemically different layers to develop within the same deposit. On Earth, a structure this old would probably be altered by water, buried by sediment, deformed by tectonics, or recycled into the mantle. The moon lacks those global processes, so impact melt created more than 4 billion years ago may still survive, although later craters have fractured, mixed, or covered much of it. Orbital images reveal frozen flows with lobed edges, smooth ponds, cracked surfaces, and places where younger impacts have punched through overlying material to expose brighter melt below. Across the far side, broad plains once interpreted as volcanic may in some cases consist partly or mainly of impact-related deposits, making careful chemical and structural measurements essential. These ancient melt sheets are scientifically valuable because their minerals began crystallizing soon after the collision that created them. Dating those minerals could establish the age of a basin and help reconstruct the timing of early bombardment, but researchers must first prove that a sample truly belongs to the original melt rather than to a later impact or volcanic event. The deposit can also preserve a blended sample of rocks excavated from different depths, offering clues about crust that no longer remains exposed in its original position. Frozen here does not mean cold liquid trapped beneath ice. It means a once flowing mass of molten stone transformed into rock and left almost motionless through an expanse of time difficult to imagine. A future explorer could stand on what appears to be an ordinary plain, while beneath the dust lies the solidified heat of an ancient catastrophe, still waiting for its crystals to reveal exactly when the moon burned there. Glass created by far-side impacts can preserve chemical clues from the early solar system. Chouchenay, droplet of lunar glass smaller than a grain of rice can preserve evidence from a collision that happened billions of years before humans existed. Impact glass forms when an asteroid or meteoroid strikes the moon with enough energy to melt part of the surface almost instantly. Some of that molten material is thrown into the airless sky as droplets, rapidly cools during flight, and returns as rounded beads or irregular shards. Because the liquid may contain several rocks melted together, its chemistry can preserve a blended sample of the impact site, including minerals that once lay beneath the visible surface. By measuring elements such as iron, magnesium, aluminium, calcium, and titanium, researchers can compare a glass fragment with known lunar terrains and estimate where its source material originated. Isotopes trapped within suitable samples can also reveal when the glass cooled, turning the fragment into a clock for the impact that created it. This is especially valuable on the far side, where ancient surfaces may contain glasses related to collisions from periods poorly represented by material previously returned to Earth. Yet these tiny archives must be interpreted carefully. Small pieces can lose gases used for dating if they are reheated by sunlight or later impacts, and an old glass can be broken, transported, or partially remelted long after its original formation. Some beads preserve mainly local ground, while others may include material carried from distant regions or even a trace of the projectile itself. Scientists therefore examine size, shape, chemistry, internal texture, exposure history, and isotopic age together rather than trusting one measurement. A reliable ancient impact glass could help reconstruct how frequently the young moon was struck and, because Earth occupied the same region of the solar system, provide indirect evidence about collisions our active planet no longer preserves. The glass does not contain a complete picture of the event, but it can retain its chemical consequences with extraordinary precision. What looks like a dark, meaningless speck may be a rapidly frozen mixture of crust, heat, and violence, holding a timestamp from an era when the inner planets were still being assembled through repeated destruction. Tiny glass beads may record ancient volcanic eruptions and violent collisions. Not every glass bead on the moon tells the same story. Even when two of them appear almost identical beneath a microscope, some were created by impacts, while others were launched from volcanic vents during eruptions that behaved more like enormous fountains than slow-moving lava flows. Volcanic beads formed when gas dissolved within rising magma expanded as the pressure fell near the surface. The magma was sprayed upward as countless droplets, which cooled rapidly in the vacuum and fell back across the landscape as layers of colored glass. Apollo 17 astronauts famously encountered orange soil containing volcanic glass beads produced more than 3 billion years ago. Their color and chemistry reflect the magma from which they formed, while traces of water, sulfur, carbon, chlorine, and other volatile substances trapped within them can reveal what the moon's deep interior once contained. Impact beads are produced differently. They form when a collision suddenly melts surface rocks and throws droplets outward, often mixing several local materials within the same glass. Scientists distinguish the two origins by studying composition, internal structure, distribution, shape, and chemical variation from the center of a bead to its edge. Volcanic beads from one eruption often form a chemically related population, while impact glasses may display a wider and less orderly mixture because the target ground was already composed of many rock fragments. The distinction matters because confusing one type for the other could create a false history of lunar eruptions or impacts. Glass can also preserve episodes that ordinary rocks hide. Recent studies of lunar samples have shown that some small glass beads may record volcanic activity much younger than the Great Lava Plains, suggesting that limited eruptions or fire fountain events continued after widespread volcanism had largely ended. Farside soil may contain its own mixture of volcanic and impact glasses, each carrying information about a different source and moment. To read them correctly, researchers must separate beads formed by magma rising from below from beads formed by objects falling from above. In one handful of lunar soil, two nearly identical spheres may therefore describe opposite journeys. One began in the Moon's interior and traveled outward, while the other began with a collision from space and was created at the surface. The soil on the far side has been ground down by micrometeorites for billions of years. The lunar soil beneath a future explorer would not be soil in the earthly sense, but the powdered remains of rock struck and reworked for an almost unimaginable length of time. The Moon has no roots to loosen its ground, no rain to soften it, and no flowing water to turn minerals into clay. Instead, its surface layer, called regolith, is produced mainly through impacts. Large collisions break bedrock into blocks, but the slow creation of fine dust is driven by an endless rain of micrometeorites, many no larger than grains of sand. These particles arrive at such high speeds that even a tiny impact can crush mineral grains, vaporize part of the target, and melt another part for a fraction of a second. Repeated over billions of years, the process reduces solid rock into angular fragments and microscopic powder. Some brief melts splash across nearby particles and weld them together into irregular glass-rich clusters called agglutinates. A later impact can break those clusters apart, mix them with fresh fragments, and bury them beneath material thrown from somewhere else. This constant overturning is known as impact gardening. It does not cultivate anything. It repeatedly stirs the surface, moving some particles downward while bringing buried material back into sunlight. The depth of the regolith varies because old highland terrain has experienced far more impacts than a relatively young lava flow. In some ancient regions it can extend for many meters, with an even deeper zone of fractured bedrock below. The finest particles remain sharp because they have not been rounded by rivers or wind, making lunar dust abrasive to seals, joints, visors, instruments, and human lungs. At the same time, the mixed soil is a valuable archive. Its grains contain pieces of nearby bedrock, distant ejecta, impact glass, implanted gases, and fragments exposed at different times. No single scoop represents one clean geological layer, because the surface has been blended repeatedly by impacts. The far side regolith is therefore both a record and a destroyer of records. It preserves ancient material while breaking, moving, and mixing the context in which that material formed. Beneath an apparently motionless landscape, the ground has been undergoing an extremely slow transformation, one microscopic collision at a time, until mountains have become dust without the help of a single drop of rain. There may be deeper layers of undisturbed lunar history beneath the far side dust. The most valuable history on the far side may not be written across the visible ground at all, but sealed inside ancient surfaces that disappeared beneath later deposits. A patch of lunar soil remains exposed for millions of years while particles from the sun, cosmic radiation, micrometeorites, and occasional fragments from distant impacts continually alter it. Then a major event can suddenly cover that surface with a thick blanket of ejecta or a new volcanic flow, cutting it off from direct exposure. The buried soil becomes what scientists call paleoregolith, an old surface preserved between younger geological layers. It is not necessarily untouched in a perfect sense. The heat of lava can alter its upper portion, and a violent impact can disturb or compress it. But material deeper within the layer may retain information that the modern surface has long since mixed together. Solar wind particles implanted into individual grains could reveal how the young sun changed its activity through time. Damage left by galactic cosmic rays might help estimate how long the layer remained exposed before burial. Tiny foreign particles could preserve traces of asteroids, comets, or even material that once escaped from Earth and later reached the Moon. Because each paleoregolith formed during a different interval, several buried layers could act like separate time capsules, preserving snapshots rather than one confused record spanning billions of years. The challenge is locating them. A smooth surface gives little indication of what lies below, and a buried layer may extend only across part of a crater or volcanic plain before being cut by later events. Orbital observations can identify promising geological boundaries, but confirming a paleoregolith would require drilling, trenching, sampling an exposed crater wall, or returning a carefully documented core. The far side may contain particularly valuable examples, because some regions preserve long sequences of ancient deposits far from the landing sites that supplied most existing lunar samples. Beneath a few meters of ordinary-looking dust, there could be a surface that once directly faced a younger sun, collected particles for millions of years, and then vanished when the next catastrophe covered it. What appears buried and forgotten may actually be better protected than anything still visible, reminding you that on the Moon, the clearest record of the past may survive precisely because it was removed from sight. Radar has revealed hidden layers beneath the surface where no human has ever walked. The far side stopped being only a surface map when radar pulses began traveling downward and returning with echoes from structures hidden beneath the rover's wheels. Lunar penetrating radar works by sending brief electromagnetic signals into the ground and measuring the energy that comes back. A pulse can move through relatively uniform material without producing a strong reflection. But when it reaches a boundary where density, porosity, rock abundance, or electrical properties change, part of the signal returns toward the instrument. By recording how long each echo takes to arrive and how its strength changes as the rover moves, scientists can build a continuous profile beneath the root, rather like revealing pages hidden below the cover of a closed book. The resulting radargram is not a direct photograph. Bright bands and curved patterns must be interpreted using laboratory measurements, geological maps, computer simulations, and assumptions about how quickly radio waves travel through lunar material. A buried boulder can produce a curved echo. A transition from fine soil to blocky debris can create a broad reflector, and a solid rock layer beneath porous material may return a particularly strong signal. Two radar frequencies allow different kinds of investigation. Higher frequency signals reveal smaller features with greater detail, but lose strength more quickly, while lower frequency signals penetrate much deeper at the cost of finer resolution. This combination allowed the Chang'e 4 mission to examine both the shallow ground and structures extending several hundred meters below von Karman crater. Radar is especially powerful on the Moon because dry material can allow radio waves to travel farther than they usually do through wet terrestrial ground. Although iron-rich minerals, rough boundaries, and scattered rocks can still weaken or confuse the echoes, researchers must also remove interference produced by the rover itself and distinguish genuine underground reflections from repeating instrumental patterns. Even with these limitations, the method has transformed an inaccessible subsurface into measurable geology. No astronaut has dug through those layers, no shaft has been opened, and no camera has looked directly into them, yet their boundaries can be traced as the rover travels overhead. The instrument does not reveal every stone or identify every mineral, but it shows that the apparently simple plane is built from separate episodes, preserved one beneath another. In a place where human eyes have never looked below the dust, radar has allowed the Moon to answer through echoes, proving that an empty-looking surface can conceal a structure far more complicated than anything visible above it. The Yutu-2 rover detected a complicated underground structure beneath the far side. What Yutu-2 found beneath von Karman crater was not one deep layer of uniform lunar soil, but a crowded geological stack assembled by impacts, quiet intervals, and repeated eruptions. Its high-frequency radar traced the upper tens of meters in fine detail and revealed a shallow section divided into materials with very different textures. Near the top lies relatively fine regolith containing scattered rocks, but deeper signals indicate increasingly blocky deposits and alternating zones of coarse and fine debris. Researchers interpret much of this material as ejecta delivered by nearby craters, especially Finsen crater and smaller impacts that repeatedly covered the landing region. The radar patterns even suggest buried crater-like structures and uneven ancient surfaces, showing that each new deposit did not fall across a perfectly level floor. Some layers accumulated over an older landscape, filled depressions, and left buried topography beneath the plane the rover sees today. The lower frequency channel reached far deeper, detecting reflectors down to roughly 330 meters. One interpretation of these data identifies at least 4 substantial basalt units, approximately 1233-34 and 96 meters thick, separated by more porous deposits that may have developed during pauses between eruptions. In this reconstruction, lava flooded the crater floor more than once, rather than arriving in a single continuous episode. During the quiet intervals, impacts added debris, and the exposed surface was gradually broken into regolith before another flow buried it. Beneath these volcanic layers, the radar detected a massive deposit beginning at roughly 230 meters and extending for more than 100 meters. Interpreted as large-scale ejecta from one or several ancient basin-forming collisions, the exact source remains uncertain because material from distant impacts can overlap, and radar reflections can sometimes support more than one geological model. Scientists have debated whether every deep band truly represents a separate lava flow, or whether some features could arise from instrumental effects, variations within one unit, or complicated buried terrain. That caution is important. U22 did not drill through the layers to confirm them directly, yet even conservative interpretations agree that the ground is not simple. Beneath the rover lies a history in which volcanic plains were interrupted by falling debris, old surfaces were buried before being destroyed, and material from distant catastrophes became part of the local foundation. The far side may look motionless now, but its underground structure reveals a place repeatedly resurfaced, paused, struck, covered, and rebuilt, until hundreds of meters of separate events were compressed beneath one quiet path. Buried ejecta layers reveal repeated impacts that happened long before human history. Chafusi. Single path across the far side can pass over the buried remains of many catastrophes without showing any clear sign of them at the surface. When an impact excavates a crater, the material it throws outward settles as an ejecta blanket composed of dust, shattered bedrock, glass, and blocks lifted from different depths. A later collision can place another blanket over the first, sealing the older deposit beneath a younger one. Repeated often enough, this process creates a layered underground record in which every band represents a separate disturbance, sometimes produced by a crater located far beyond the local horizon. At the Changi 4 landing site inside Von Karman crater, radar observations indicate that the subsurface contains several zones of differently sized debris rather than one uniform deposit. Researchers have linked some shallow material to ejecta from nearby Finsen crater, although other impacts almost certainly contributed to the mixture. The internal texture of each layer offers clues about its origin. A coarse zone filled with large blocks may have fallen close to a powerful impact, while a finer layer may represent more distant debris or soil that developed during a long quiet interval before being buried. Boundaries between deposits can also preserve the shape of older ground, including shallow depressions and crater floors that vanished beneath later material. Scientists reconstruct the sequence by combining radar profiles with orbital maps, crater positions, ejecta directions, and estimates of how material thins with distance from its source. They cannot assign every underground fragment to a specific crater with certainty, because later impacts stir the upper layers and different ejecta blankets can overlap. Yet the broad pattern is unmistakable. The ground was repeatedly covered, exposed, disturbed, and covered again. These buried deposits allow researchers to study impacts that have lost much of their visible expression, revealing not only that collisions occurred, but how their debris traveled and altered distant landscapes. Human history occupies only a vanishingly thin moment compared with this sequence. Beneath the rover's quiet tracks lie layers formed. While Earth itself was passing through geological ages no observer witnessed. The far side subsurface is therefore not simply broken rock beneath dust. It is a vertical history of falling worlds, with each buried blanket preserving the aftermath of a different sky that once erupted above the moon. Ancient lava may be hidden beneath crater debris, where the surface now looks completely dry. A landscape can appear pale, rough, and entirely non-volcanic, while an ancient lava plain remains concealed only a short distance below it. Scientists call these hidden basaltic deposits cryptomaria, meaning lunar seas that have been buried from view. They formed when lava reached the surface early in lunar history and spread across low terrain, producing dark volcanic plains similar in origin to visible maria. Later, basin-forming impacts and younger craters covered those plains with brighter debris excavated from the highlands, changing the color and texture of the landscape so completely that the volcanic foundation could no longer be recognized in ordinary photographs. The buried lava is discovered indirectly. A younger crater may punch through the pale covering and excavate darker basalt from below, surrounding itself with a dark halo that does not match the visible surface. Spectrometers can then detect iron-rich and pyroxene-bearing material, typical of basalt within that halo. Gravity measurements may also reveal dense volcanic rock beneath lighter deposits, while subtle topographic patterns can preserve the outlines of flows or buried basin floors. Evidence for cryptomaria has been identified in several lunar regions, including the far side area around Dewar Crater, where researchers found signs of old low titanium basalt concealed beneath later ejecta. Such discoveries suggest that early volcanism may have been more widespread than the surviving dark plains imply. The visible moon records only eruptions that remained exposed. It hides those that were covered before modern observers could see them. This matters because buried flows can extend the known volcanic timeline backward and reveal mantle melting in regions that now appear to be ordinary highlands. Their chemistry may also differ from younger surface basalts, preserving magma produced under earlier internal temperatures and pressures. Yet scientists must avoid interpreting every dark halo crater as proof of hidden lava. Some impacts excavate darker non-volcanic rocks, and space weathering can alter color contrasts. Confirming a cryptomare requires several independent lines of evidence rather than appearance alone. The completely dry-looking surface is therefore not deceptive because it once held water. It is deceptive because its latest layer hides an older landscape. Beneath pale crater debris may lie a black volcanic plain that flowed across the far side, cooled, and disappeared from sight when the moon placed a newer history on top of it. Possible lava tubes could exist beneath rare volcanic regions on the far side. Somewhere beneath a far-side lava plain, an empty tunnel may follow the path of a river of molten rock that vanished billions of years ago. Lava tubes form when the exposed surface of a flowing lava channel cools and hardens, while hotter liquid continues moving underneath. The solid roof insulates the interior, allowing lava to travel farther than an open flow could remain molten. When the eruption weakens, the remaining liquid can drain away, leaving behind a long cavity enclosed within basalt. Such structures exist on Earth, and lunar pits photographed from orbit provide strong evidence that similar caves occur on the moon. Some pits widen below their openings, consistent with sections of roof collapsing into a larger hidden space. Most well-known candidates are associated with extensive volcanic terrain on the near side, but the physical process was not restricted to that hemisphere. Rare far-side volcanic regions, including isolated maria and basalt-filled craters, once carried moving lava and could therefore have produced tubes where flows remained sufficiently steady, fluid, and thick. The difficulty is proving that any specific far-side cavity exists. A tube with an intact roof may leave almost no visible trace, while a narrow pit could be confused with an impact-related collapse or a void inside solidified impact melt. Researchers search for unusual pit shapes, sinuous channels, subtle surface ridges, temperature differences, gravity anomalies, and radar reflections that might indicate empty space underground. New concepts for orbital penetrating radar aim to survey the lunar subsurface more widely, after which rover-based radar could examine promising sites at much higher detail. Even then, an unusual echo would need careful modeling because rock boundaries and buried boulders can imitate the signal of a cavity. No explorer has entered a confirmed far-side lava tube, so these structures must remain possibilities rather than established landmarks. If one is eventually found, its scientific importance would extend beyond the empty space itself. Protected walls could preserve the internal structure of an ancient flow, minerals less altered by surface radiation, and perhaps traces of gases once carried by lunar magma. Layered lava exposed inside the tunnel might reveal whether several eruptions use the same underground route. The far side's volcanic regions are rare, but rarity does not make their hidden plumbing simple. A small dark plain may be only the visible end of a much larger system, with part of its history still enclosed inside tunnels that have remained silent since the final lava drained away. Underground cavities could protect future explorers from radiation and extreme temperatures. The safest place for future explorers may not be on the moon's surface at all, but beneath a roof of ancient volcanic rock. With almost no atmosphere and no strong global magnetic shield, the exposed lunar ground receives energetic particles from the sun and from distant cosmic sources that can pass through human tissue, damage cells, and gradually increase the risk of serious illness. A powerful solar eruption could deliver a dangerous dose within a short period, forcing astronauts to reach a heavily shielded shelter quickly. Thick cave walls could solve part of this problem naturally. Several meters of rock above an underground chamber would absorb or scatter much of the incoming radiation before it reached a habitat, reducing the amount of shielding that crews would need to transport from Earth or construct from loose lunar soil. The same roof could protect against micrometeorites, tiny objects that cross space at extreme speed and strike the moon without being slowed by air. Although most are small, a surface base must still be designed to survive their repeated impacts. Temperature is another reason to look underground. On the open surface, exposed ground becomes intensely hot during the long lunar day and extremely cold during the equally long night. Observations of some lunar pits show that shaded interiors can maintain far more stable temperatures than the surface above, suggesting that deeper caves may offer a comparatively moderate environment for equipment and people. Stability would reduce the stress placed on batteries, seals, electronics, and habitat walls that would otherwise expand and contract through severe thermal cycles. Yet a cave would not become a ready-made home simply because it offers protection. Engineers would first need to map its depth, roof thickness, internal shape, and structural stability. Loose blocks could fall, steep entrances might be difficult to cross, and radio communication could weaken inside solid rock. Habitats would still require pressure, breathable air, reliable lighting, power, emergency exits, and careful control of abrasive dust carried in by explorers. No confirmed far-side lava tube has yet been entered, so proposals remain based on orbital evidence, terrestrial comparisons, and engineering studies rather than direct inspection. Even so, the possibility changes how you imagine lunar settlement. The first lasting base may not stand proudly beneath the black sky, like a city displayed to space. It may survive by becoming almost invisible, placed inside a cavity formed by an eruption billions of years earlier, where the moon itself provides the walls that protect fragile human life from the environment above. The far side contains strange magnetic regions, even though the moon has no global magnetic field. Our compass on the moon would not point toward one dependable magnetic north. Yet a sensitive instrument crossing the far side could suddenly enter a small region where the surrounding crust produces a measurable magnetic field of its own. The modern moon lacks the powerful planet-wide field generated by Earth's moving liquid core, but magnetometers carried by orbiting spacecraft have mapped a patchwork of localized magnetic anomalies embedded within particular areas of lunar rock. These fields are weak compared with Earth's global magnetosphere and do not surround the entire Moon. But some are strong enough to alter how charged particles from the solar wind approach the surface. Where an anomaly is concentrated, magnetic forces can redirect part of that particle flow, creating a miniature and incomplete protective bubble, sometimes described as a mini magnetosphere. It cannot shelter an entire hemisphere, and it would not provide astronauts with reliable protection from all forms of radiation, but it can change the local interaction between space and the lunar soil. Spacecraft detect these regions in several ways. A magnetometer measures changes in the field directly, while instruments studying electrons can infer hidden magnetism from the way charged particles are reflected or redirected above the surface. Some anomalies occur near bright, winding markings called lunar swirls, suggesting that magnetic shielding may slow the darkening effects of the solar wind in those locations. Others are associated with regions affected by large impacts, although the connection is not simple enough to prove that every collision created the magnetism beneath it. The fields also vary in shape and direction, showing that they do not belong to one organized global system. Instead, each patch behaves more like a magnetized piece of crust, preserving its own orientation. This makes the far side magnetically uneven in a way the eye cannot see. Two neighboring regions may look almost identical in photographs while interacting differently. With particles arriving from the sun, scientists are still testing whether certain anomalies were produced mainly by ancient internal fields, impact-related processes, or a combination of both. The strangeness lies not in the Moon secretly possessing a hidden global magnetosphere, but in its ability to retain isolated magnetic islands after the larger field disappeared. The world as a whole is nearly magnetically silent, yet pieces of its crust continue to disturb the solar wind, like scattered instruments still vibrating after the orchestra that once guided them has stopped playing. Some hidden areas may still preserve remains of the Moon's ancient magnetic past. Buried inside certain far-side rocks may be a fossil record of an invisible shield that surrounded the young Moon and then vanished. When molten or intensely heated rock cools, tiny magnetic minerals within it can align with the field present at that time. Once the material falls below a critical temperature, part of that alignment can become locked into the rock, preserving both the strength and approximate direction of the ancient field long after the field itself has disappeared. Apollo samples carry remnant magnetization, and many scientists interpret this evidence as a sign that the early Moon once generated a global magnetic field through a dynamo operating within its metallic core. The exact history remains debated. Some studies suggest that the lunar field may once have approached the strength of Earth's modern field and persisted in weaker form for more than 1 billion years, while other researchers question whether all strong signals truly came from a long-lasting core dynamo. Impacts complicate the record because shock waves can erase an earlier magnetic signature, reorient minerals, create temporary plasmas capable of amplifying surrounding fields, or heat rock enough for it to record a newer event. This makes location and age essential. A sample must be placed within its geological context before scientists can decide whether its magnetism was acquired while cooling from magma during a basin-forming collision or through a later disturbance. Ancient far-side terrain may offer valuable evidence because some of its crust formed early and avoided the extensive volcanic resurfacing seen elsewhere. If rocks from several hidden regions can be dated and their magnetic directions compared, researchers may determine when the lunar dynamo began, how its strength changed, and when the core lost the energy needed to sustain it. The answer could reveal how the Moon's interior cooled, whether gravitational interactions with Earth helped stir its core, and how impacts influenced the final decline of the field. It could also clarify whether the young Moon once possessed a magnetosphere large enough to interact with Earth's own magnetic environment. No surviving anomaly can replay that vanished shield directly, but magnetized minerals can preserve fragments of its history. The field itself left no crater, mountain, or visible horizon. It disappeared without leaving a shape you could photograph. Yet the alignment of microscopic grains may still hold its memory, allowing a stone collected from the hidden hemisphere to describe an era when the moon was not the magnetically quiet world it is today. Bright lunar swirls appear on parts of the far side without any clear volcanic cause. Some of the moon's brightest markings refuse to behave like ordinary geological features. Known as lunar swirls, these pale ribbons and patches curve across portions of the far side without forming hills, trenches, hardened flows, or obvious layers of erupted material. Detailed images and elevation measurements show that the bright patterns are usually only surface markings. The ground inside a swirl may sit at almost exactly the same height as the darker soil beside it, as though the landscape had changed color without changing shape. This immediately separates swirls from many familiar lunar formations. Lava usually follows low ground and leaves recognizable flow boundaries. Impact ejecta spreads outward from a crater and commonly fades with distance. A landslide descends a slope and deposits material below. Swirls can cross different kinds of terrain without obeying these simple controls, appearing on both dark basalt and bright highland crust, and at a wide range of elevations. Several explanations have been proposed. A comet passing close to the moon might blast away darkened surface dust with gas and fine particles, uncovering brighter material beneath. Electrically charged dust could be lifted and sorted across the surface, concentrating finer grains in winding patterns. The strongest modern explanation connects swirls with magnetized areas of the crust that change the way solar particles reach the ground. Yet even this relationship does not close the mystery. Every well-established swirl is associated with a magnetic anomaly, but many magnetic anomalies have no visible swirl at all. This means magnetism may be necessary without being sufficient. The field's shape, the age and composition of the soil, the local impact history, and the direction of incoming solar particles may all influence whether a bright pattern develops. No plume has been observed creating one, and no return sample has yet allowed scientists to stand inside a swirl and test its soil directly against neighboring ground. The far side swirls therefore remain unusual, not because they require a supernatural cause, but because several normal physical processes may be interacting in a combination we have not fully reconstructed. Their brightness is a clue without a visible structure beneath it, asking how the moon can redraw its surface while leaving the landscape itself almost untouched. The mysterious swirls of Mare Ingenii look as though the surface has been painted. Across the floor of Mare Ingenii, pale lines curl through dark ground with such delicacy that they look less like rock formations than brushstrokes left by an unseen hand. One of the best-known patterns bends into a shape often compared with the Greek letter omega, while narrower bright strands separate, reconnect, and border darker lanes across the volcanic plain. Their appearance becomes even more remarkable when the surrounding geology is considered. Mare Ingenii contains basalt that once flooded part of Thompson crater, leaving sections of the older crater rims standing above the lava like islands of ancient terrain. These surviving high areas are called kipukas on Earth, when older land remains surrounded by younger lava. The swirl does not behave as though it was simply created by the eruption that formed the mare, nor does it follow every ridge and depression left by Thompson. High-resolution topographic studies show no matching ridge beneath the bright lines, and no channel carved beside them. If you crossed from a dark lane into a bright ribbon, you might not feel any clear rise or drop beneath your feet. The transformation exists mainly within the uppermost grains of lunar soil, where differences in reflectivity make one region shine more strongly than another. This is why the painted comparison is so effective. Paint changes the appearance of a wall without changing its architecture, and the Mare Ingenii swirls seem to alter the optical skin of the moon while leaving the underlying terrain continuous. Their twisting boundaries are also too organized to dismiss as random patches of fresh dust. They appear connected to the complicated geometry of the magnetic field below, although the field itself is invisible and cannot be photographed as a set of lines. The visible pattern may therefore be a surface translation of something happening above and beneath the soil. Charged particles being redirected, some areas aging slowly and neighboring areas changing faster. Marangini teaches you that a planetary landscape does not always need to move, erupt, or collapse in order to acquire a new form. Sometimes the change is confined to the way light returns from the ground. Yet that thin alteration is enough to create one of the most beautiful and difficult to explain images on the hidden moon. Local magnetic fields may shield. These swirls from the solar wind, the moon may have drawn its swirling patterns with an invisible stream of particles arriving continuously from the sun. The solar wind carries electrically charged protons and electrons through space, and because most of the lunar surface lacks strong magnetic protection, those particles strike the exposed soil directly. Over long periods, they contribute to space weathering, a set of processes that gradually changes the optical properties of lunar grains. Solar particles become implanted in minerals, while micrometeorite impacts melt and vaporize tiny portions of the soil. Some of that vapor condenses as extremely small particles of metallic iron within glassy coatings and fused grains. As these products accumulate, mature lunar soil generally becomes darker and its reflected spectrum changes. A localized magnetic anomaly can interfere with this process. The field bends the paths of incoming charged particles, reducing the solar wind flux reaching certain patches while redirecting or concentrating particles along nearby boundaries. The protected ground then weathers more slowly and remains relatively bright, while adjacent areas receiving a stronger particle flow may darken more rapidly. Studies of Marangini suggest that the swirls are not freshly uncovered surfaces. Instead, their soils display signs of reduced weathering compared with neighboring regions, supporting the idea that brightness can be preserved rather than newly created. Computer simulations have also reproduced swirl-like light and dark patterns by modeling how the solar wind encounters complex crustal magnetic fields. The result resembles a miniature and highly uneven umbrella. Some locations lie beneath its protection, while particles are funneled toward the edges. But the shield is incomplete. Cosmic rays and micrometeorites still reach the ground, and the fields are far too small and weak to make a swirl safe for unprotected astronauts. Magnetism also cannot be the only ingredient, because some strong anomalies lack obvious bright markings. The strength, direction, and geometry of both magnetic and electric fields appear to matter, along with the condition of the soil receiving the particles. This is why the shielding model is powerful without being final. It explains how invisible fields can preserve brightness and create darker borders, yet it still leaves scientists asking why only certain magnetic regions become works of surface art. The swirls may be the moon's record of solar weather, not written by wind-moving dust across the ground, but by charged particles being quietly guided around patches of ancient rock. The far side could help explain why the moon's ancient magnetic field disappeared. The final heartbeat of the moon's ancient magnetic field may be recorded in rocks that have never been collected from the regions where the field's decline was most clearly preserved. Today the moon has no powerful global magnetosphere, yet magnetized samples returned by the Apollo missions show that its interior once generated a much stronger field, probably through a dynamo involving motion inside its small metallic core. The unanswered question is not simply whether that dynamo existed, but what kept it alive and why it eventually failed. A planetary dynamo needs energy to move electrically conducting liquid. On the young moon, heat escaping from the core may initially have driven convection, while the gradual solidification of an inner core could later have released heat and changed the distribution of lighter elements in the remaining liquid. Other models suggest that Earth's gravity helped stir the lunar interior when the moon orbited much closer, or that changes in the moon's rotation caused its mantle and core to move differently. None of these energy sources would have remained equally powerful forever. As the moon cooled, its interior lost heat. As it moved farther from Earth, gravitational stirring weakened. Once the motion inside the core became too slow or too orderly, the dynamo could no longer maintain a global field, leaving only magnetism frozen into older crust. Farside rocks could help separate these possibilities because they come from geological environments and ages not adequately represented by the Apollo collection. A precisely dated rock can reveal whether a strong field existed when it cooled, while a younger rock from the same region may record a weaker field or none at all. Samples from ancient Farside basins could also show whether enormous impacts briefly disturbed the core, strengthened an existing dynamo, or created local magnetic signatures that have been mistaken for evidence of a global field. This distinction is crucial because an impact can heat and remagnetize rock without proving that the entire moon was magnetically active at that moment. Scientists need samples whose original orientation and geological setting are carefully documented, not isolated stones whose histories have been mixed by later collisions. A sequence of such rocks could turn the disappearance of the field from a vague decline into a timeline, showing whether the dynamo faded gradually, stopped suddenly, or weakened and restarted before dying permanently. The hidden hemisphere may therefore preserve more than scattered magnetic anomalies. It may contain the missing intervals in the life of the lunar core, allowing you to ask when the moon ceased generating an invisible shield and became the magnetically quiet world that circles Earth today. Solar wind constantly alters the hidden surface atom by atom. Nothing appears to move across the far side landscape, yet an invisible stream from the sun is changing its uppermost grains every second. The solar wind is a flow of charged particles dominated by protons and electrons, traveling outward through the solar system and striking the moon almost directly because there is no thick atmosphere to stop them. Each particle carries little energy compared with a large impact, but the attack never truly ends. When energetic ions enter a grain of lunar soil, they can displace atoms from their positions, damage the orderly crystal structure, and create a thin, disturbed rim around the particle. Some collisions transfer enough energy to knock surface atoms completely free, a process called sputtering. Those released atoms may escape the moon, briefly enter its extremely thin exosphere, or settle somewhere else after traveling above the ground. Solar wind hydrogen can also become implanted within minerals containing oxygen. Under suitable conditions, that hydrogen can contribute to the formation of hydroxyl and molecular water, although some of it is later released as the surface heats during lunar daytime. The amount retained depends on temperature, mineral type, latitude, exposure history, and the changing intensity of the solar wind. This means the moon's surface is not chemically sealed, even though it has no rain, rivers, or ordinary weather. At the scale of individual atoms, material is continually added, displaced, removed, and rearranged. Solar storms can temporarily intensify the process by delivering larger numbers of energetic particles, while the moon's passage through Earth's extended magnetic environment changes the particle population reaching it. Local magnetic anomalies can redirect part of the flow, causing neighboring patches of ground to experience different exposure despite lying within the same landscape. Over time, these differences affect the microscopic structure and chemistry of the soil, influencing how scientists interpret observations made from orbit. A mineral grain altered at its surface may reflect light differently from an unexposed fragment of the same rock. And implanted hydrogen can complicate attempts to determine whether lunar water came from the interior, impacting objects, or the sun. The far side may look like a preserved ancient world, but preservation does not mean complete stillness. Its mountains and craters change slowly, while their exposed atoms participate in a continuous exchange with space. The solar wind is too faint for you to feel and too diffuse for you to see, yet across billions of years, it has touched almost every unprotected grain, quietly proving that even the vacuum above the moon is not an empty environment. Radiation slowly darkens lunar soil through a process called space weathering. The moon's surface grows old in color long before its rocks lose their shape. Scientists call this gradual transformation space weathering, a collection of microscopic processes driven mainly by solar wind irradiation, energetic particles, and the constant impacts of tiny meteoroids. The word weathering can be misleading because there is no rain washing minerals apart and no air carrying sand across the ground. Instead, exposed soil is modified through brief flashes of heat, atomic collisions, melting, vaporization, and chemical reduction. When micrometeorites strike, they can melt several nearby grains and weld them into irregular glassy particles known as agglutinates. Part of the vaporized material then condenses as extremely thin coatings on surrounding grains. Within these coatings and glasses, iron that was originally bound inside minerals can be reduced into tiny particles of metallic iron, many far smaller than a wavelength of visible light. These nanophase iron particles strongly alter the way the soil interacts with sunlight. As they accumulate, the surface generally becomes darker, takes on a redder spectral slope, and loses some of the clear absorption features scientists use to identify minerals from orbit. The underlying rock has not necessarily changed into a different geological material, yet its optical signature can become muted enough to disguise what it contains. This creates a serious problem for lunar mapping. Two surfaces made from similar rock may appear different if one has remained exposed much longer, while two chemically different terrains may begin to look more alike after both become mature. Researchers therefore compare brightness, spectral shape, crater relationships, and laboratory studies of returned soil rather than treating color as a direct measure of composition. Radiation contributes by damaging crystal structures and helping drive chemical changes at grain surfaces, but it is not acting alone. Micrometeorite heating and solar wind implantation are essential parts of the same long process. Nor does every region darken at exactly the same rate. Mineral content, grain size, local magnetism, burial, and later excavation all affect how quickly optical maturity develops. A surface can also be repeatedly reset when an impact exposes material that has spent ages protected underground. Although the broader science of fresh crater brightness belongs to the next part of the story. What matters here is that the moon's familiar grey appearance is not simply the original colour of untouched rock. It is partly the accumulated result of exposure, a coating of time created grain by grain. The hidden hemisphere has no atmosphere to produce clouds or storms, yet it has been weathered continuously by space itself, becoming darker not through decay in the earthly sense, but through countless microscopic encounters with particles and dust arriving from the sky. Fresh craters look brighter because they expose material that has not yet been darkened. A newly formed crater can shine against the far side, like a wound that has not yet learned how to hide itself. The brightness does not usually mean the impact created a new white mineral or heated the ground until it began to glow. Instead, the collision cuts through the mature upper soil and throws less weathered material outward from below. This freshly exposed rock reflects sunlight differently from the surface that had spent immense periods facing space. So the crater walls, rim, and ejector can appear much brighter than the surrounding landscape. The most dramatic young craters also produce rays, long, pale streaks of excavated material stretching far beyond the rim, sometimes crossing terrain that is chemically different from the crater itself. Their visibility becomes a useful clue to relative age. A sharp crater with crisp edges, few smaller impacts on top of it, and a clear ray system is generally younger than a softened crater whose bright deposits have faded into the background. Yet brightness alone cannot provide an exact date. A crater excavating naturally pale highland rock may look brighter than one formed in darker basalt, and lighting conditions can exaggerate or conceal contrast. Scientists therefore compare color with shape, overlapping features, surface texture, and the number of later craters superimposed upon the ejector. Over time, the brilliant pattern weakens. Tiny impacts stir darker, mature soil into the fresh deposit. Solar particles alter the exposed grains, and later debris gradually blurs the boundary between the crater and its surroundings. The rays do not vanish in one moment. They become less distinct until the impact no longer stands apart from the ancient terrain. This allows you to see lunar time in a way no clock could display. A bright crater is not young because its underlying rock formed recently. Much of that rock may be billions of years old. It is young because the material has only recently been uncovered and placed under the open sky. The moon can therefore make ancient stone look new again, not by creating it, but by turning over its surface and exposing a layer that had been sheltered from space. Every bright scar is a temporary contrast between two kinds of age: the deep age of the rock itself and the much shorter age of its exposure. Every new impact temporarily reveals a younger layer beneath the ancient surface. Each new impact opens a brief geological window, allowing buried material to appear before the lunar environment slowly disguises it again. The phrase "younger layer" must be understood carefully, because the rock beneath the surface may actually be older than the soil covering it. What becomes younger is its exposure history. Before the collision, that material may have remained protected from direct radiation, solar particles, and constant micrometeorite disturbance. The impact suddenly excavates it, lifting fragments from below the crater and distributing them across the rim and surrounding ejecta blanket. The depth reached depends on the size and form of the crater, but excavation does not simply scoop out everything down to the final floor. Material moves along curved paths during crater formation, and much of the exposed subsurface originates from depths shallower than the crater's completed appearance might suggest. This is why scientists use fresh craters as natural probes. A small crater can reveal the boundary between loose regolith and stronger bedrock. A larger crater may penetrate a buried lava flow, impact melt sheet, or ancient ejecta layer, bringing material with a different color or chemical signature into view. By comparing the crater's fresh deposits with the unchanged terrain around it, researchers can infer what lies below without drilling. Dark halo craters, for example, may expose hidden basalt beneath brighter covering material, while unusually bright ejecta can indicate pale crust concealed under a darker surface. The opportunity is temporary because the exposed layer immediately begins entering a new stage of alteration. Its sharp fragments are disturbed by later impacts. Its optical character changes under prolonged exposure, and loose material slides down crater walls until the original excavation pattern becomes harder to interpret. A crater therefore reveals the subsurface most clearly soon after it forms, then gradually closes the window through the same slow processes affecting the rest of the moon. This creates a quiet paradox. An impact destroys the original arrangement of the ground, yet that destruction may be the only reason a hidden layer can be studied at all. When you see a fresh crater, you are not merely looking downward into a hole. You are looking sideways through lunar history, because material once separated vertically has been lifted and spread across the surface, where its differences can finally be read. The moon blocks Earth's radio signals from reaching most of the far side. Turn a radio antenna toward Earth from deep within the lunar far side, and the loudest technological planet nearby becomes astonishingly difficult to hear. The reason is not that Earth stops transmitting, or that the moon absorbs every signal perfectly. It is geometry. Radio waves generally travel outward along paths that require a clear route between transmitter and receiver, and the solid lunar globe interrupts that route across most of the hidden hemisphere. A surface antenna near the center of the far side sits well below the radio horizon, with thousands of kilometers of rock between it and terrestrial transmitters. Broadcasts, radar, navigation signals, and much of the interference surrounding Earth cannot travel directly through that barrier. This produces a broad zone of radio shadow, but the boundary is not perfectly sharp. Long radio waves can bend slightly around the lunar limb through diffraction, and the strength of this leakage changes with frequency. Signals may also arrive indirectly after being scattered through the plasma environment around Earth, or transmitted by satellites located high enough to remain visible above the moon's edge. This is why scientists say the moon shields most of the far side, rather than declaring the entire hemisphere absolutely silent. A telescope placed near the outer margins would receive less protection than one positioned deep within the blocked region, and an instrument on a mountain or orbiting high above the surface might regain a direct view of Earth. The Moon's gentle apparent rocking also means that narrow areas near the boundary can sometimes move into and out of terrestrial visibility. For observatory design, every kilometer and every frequency matter. Engineers must calculate where Earth remains hidden, how much diffraction reaches the site, whether communication satellites introduce new interference, and when the Sun may become another powerful radio source. During the lunar night, a deep far-side location can be shielded from Earth, while the Moon itself also blocks the Sun, creating an especially rare listening interval. Yet that silence is fragile. A nearby relay transmitter, navigation beacon, rover, or poorly shielded computer could contaminate frequencies that the natural lunar barrier had protected for billions of years. The Moon gives humanity a remarkable radio wall without requiring us to build one, but it does not guarantee that the quiet will survive our arrival. The strange question is no longer whether the far side can hide from Earth's noise. It is whether we can explore that silence without carrying enough noise with us to erase it. Even weak radio transmissions from Earth can disappear behind the Moon's solid body. A transmitter does not have to fall silent for its signal to vanish. It only has to move behind the Moon from the receiver's point of view. This effect is called lunar occultation, and it provides one of the clearest demonstrations that radio waves, despite being invisible, still obey the physical geometry of obstacles. Imagine a spacecraft carrying a radio receiver as it passes from the Moon's Earth-facing side toward the hidden hemisphere. At first, terrestrial signals remain detectable. Then the curve of the lunar horizon begins covering Earth, and individual transmissions weaken as their direct paths are removed. Once the receiver moves deeply into the shadow, even signals that were previously obvious can sink beneath the background noise. The Moon does not need to absorb them perfectly. Its solid body is simply too large for the direct waves to pass through, while only a much smaller amount of energy can bend around the edge through diffraction. Longer wavelengths bend more effectively than shorter ones, so the depth of the radio shadow changes with frequency rather than remaining identical across the spectrum. The boundary also shifts with altitude. An antenna on the surface loses sight of Earth sooner than a receiver orbiting high above it, because the elevated instrument can see over more of the lunar curve. NASA's Radio Astronomy Explorer 2, placed in lunar orbit in 1973, used repeated occultations to investigate very low-frequency cosmic radio sources. As the Moon moved between the spacecraft and a source, the changing signal helped scientists estimate where that source lay in the sky and how large it appeared. The same principle explains why weak terrestrial transmissions can disappear so dramatically behind the Moon. Their weakness is not what causes the disappearance. Even a powerful direct signal can be blocked when the geometry is complete. Weak signals simply fall below detection sooner because the small amount that leaks around the limb may be indistinguishable from natural radio noise. This creates an unusual experience for an instrument moving behind the Moon. Earth remains physically close, filled with transmitters broadcasting in every direction. Yet its electromagnetic presence fades as though someone were slowly closing a massive stone door. The signal has not ceased to exist, and the transmitting station has not changed. The Moon has merely entered the line between sender and listener, showing that communication across space depends not only on distance and power, but on whether 2 points can still see one another through the invisible pathways of radio light. Low-frequency signals that cannot reach ground telescopes could be detected there. An entire region of the cosmic radio spectrum reaches Earth and then disappears above our heads, blocked before any ground telescope can receive it. The barrier is the ionosphere, a high layer of electrically charged particles produced when sunlight interacts with the upper atmosphere. Depending on conditions, this layer can bend, reflect, distort, or completely prevent very low-frequency radio waves from reaching the surface. Frequencies below roughly 10 to 30 megahertz are especially difficult, although the exact boundary changes with time of day, solar activity, location, and atmospheric conditions. This is why building a larger antenna on Earth cannot solve the problem. Greater sensitivity is useless when the desired radiation never reaches the instrument. A telescope on the Moon would sit beyond the terrestrial ionosphere and could observe wavelengths longer than 10 meters, opening a part of the sky that humanity has explored only in limited ways with spacecraft. These signals may come from energetic electrons moving through magnetic fields, plasma disturbances in the solar wind, powerful eruptions from the sun, radio bursts around planets, and perhaps auroral activity associated with planets orbiting other stars. Long wavelength observations could reveal how charged particles behave in environments that cannot be studied through ordinary visible light. Yet receiving such waves requires an instrument very different from a familiar optical telescope. The antennas may be simple metal wires or dipoles laid across the ground, but many of them must work together because long wavelengths provide poor detail unless the collecting system is spread across an enormous area. A single antenna can measure how radio brightness changes with frequency, while a large array can compare the arrival time of the same wave at separate locations and gradually construct an image. The lunar surface provides a stable foundation for such a network, although dust, temperature changes, power demands, and self-generated electrical interference would make construction difficult. Concepts such as NASA's proposed Farview Array envision tens of thousands of antennas covering a vast area and operating at frequencies from about 5 to 40 megahertz. Other designs would suspend a mesh inside a crater to create one immense collecting surface. These are proposals rather than completed observatories, but they illustrate why the far side is scientifically valuable for more than its quietness. It grants access to wavelengths that the atmosphere has always hidden from ground-based astronomy. From Earth, that part of the universe is not merely faint, it is physically inaccessible. A lunar instrument could therefore detect no new kind of energy, only ancient radio light that has been arriving all along, waiting beyond an atmospheric curtain that human eyes and ground telescopes cannot cross. A far-side telescope might listen to the universe before the first stars existed. Before the first star ignited, the universe had no galaxies shining in visible light, yet it was not silent. Space was filled mainly with hydrogen, helium, dark matter, and the fading radiation left from the early cosmos. Gravity was already gathering matter into slightly denser regions, preparing the structures from which stars and galaxies would eventually emerge. But there were no luminous objects available to photograph this process. A far-side radio telescope could investigate that unseen era by measuring how neutral hydrogen interacted with the cosmic microwave background, the ancient glow that filled all of space behind it. Hydrogen naturally responds at a radio wavelength of 21 centimeters, but expansion has stretched radiation from the Dark Ages into much longer wavelengths that now arrive at very low frequencies. The telescope would not hear a clear pulse or message from one location. It would search for an extraordinarily faint change in radio brightness spread across the sky and hidden beneath much stronger foreground radiation from the Milky Way. One type of measurement would examine the average signal at different frequencies, allowing scientists to reconstruct how the temperature of cosmic gas changed through time. A much larger array could measure tiny variations from one direction to another, creating a statistical map of matter before stars began disturbing the hydrogen around them. Those variations could reveal how the earliest density patterns grew under gravity and whether the standard model of cosmic evolution accurately describes an era we have never directly observed. Because the Dark Ages occurred before complicated astrophysical objects filled the universe with heat and radiation, the signal may offer an unusually clean test of fundamental physics. It could help researchers investigate the behavior of dark matter, the expansion history of the young universe, the influence of neutrinos, and the primordial fluctuations that may have been produced during cosmic inflation. Some proposed effects are subtle and uncertain, so a detection would need to be separated carefully from instrumental noise, lunar environmental effects, and radio emission many thousands of times brighter than the desired signal. This is why a small pathfinder and a giant imaging array would serve different purposes. The first could characterize the environment and seek the broad spectral feature, while the second might eventually map how ancient hydrogen was distributed across three-dimensional cosmic space. What such an observatory would recover is not the light of the first stars, but the conditions that made those stars possible. You would be listening to the universe while it was still dark, when gravity was quietly gathering invisible clouds, and the future architecture of galaxies existed only as small variations in a sea of hydrogen. The signal would be faint, but its meaning would be immense, a record from the last great period of cosmic history that no conventional telescope has yet been able to see. Ancient hydrogen signals could reveal what happened during the cosmic dark ages. Hydrogen may have preserved a record of the universe from a time when there were no stars to illuminate what was happening. In its neutral form, each hydrogen atom contains a proton and an electron whose tiny magnetic orientations can either align or oppose one another. On rare occasions, the relationship between them changes, allowing the atom to absorb or release radio energy at a natural wavelength of 21 centimeters. Radiation produced during the cosmic dark ages has traveled through expanding space for more than 13 billion years, stretching that original wavelength until it reaches us today as extremely long, low-frequency radio waves. The strength of the signal depends on the temperature of the hydrogen compared with the background radiation surrounding it. If the gas was colder than that ancient background glow, it absorbed some of the radio light and left a faint dip in the spectrum. If it later became warmer, it could produce a weak emission signal instead. By measuring how this pattern changes across frequency, astronomers could reconstruct a sequence of cosmic events, because each frequency corresponds to radiation released during a different stage of expansion. The earliest portions could reveal how ordinary matter cooled after separating thermally from the background radiation, while later changes could show when gravity began concentrating gas around invisible dark matter structures. Scientists could test whether the gas cooled exactly as standard cosmology predicts, or whether an unknown interaction removed additional heat. Some theories propose that collisions between ordinary matter and certain kinds of dark matter might have changed the hydrogen temperature, leaving a detectable imprint. Other features could reveal the influence of early magnetic fields, unusual forms of energy, or small variations produced during the universe's first moments. The signal would not identify individual clouds as clearly as a photograph identifies a galaxy. Researchers would first seek its average shape and then study subtle fluctuations across the sky, using them to map how matter gathered before luminous objects complicated the environment. This is difficult because radio emission from the Milky Way is enormously brighter than the ancient hydrogen pattern, requiring exceptional calibration and a deep understanding of every instrumental effect. Yet the reward is unique. The cosmic microwave background shows the universe when it was about 380,000 years old, while ordinary telescopes reveal it after stars and galaxies appeared. Between those records lies an immense observational gap. Ancient hydrogen could fill that gap, allowing you to follow the universe through its long, unseen adolescence, when darkness was not emptiness, but a quiet medium in which the first large structures were slowly taking form. Giant Crater could one day be turned into a natural radio telescope dish. One of the moon's empty craters could become the supporting frame for the largest filled radio telescope ever constructed. But the crater itself would not simply begin collecting signals like a bare stone bowl. NASA's studied lunar crater radio telescope concept proposes selecting a far-side crater roughly 3 to 5 kilometers wide with a shape suitable for holding an enormous reflecting mesh. Robotic vehicles would descend or anchor themselves along the steep inner walls, stretch cables across the depression, and suspend a network of conductive wires about 1 kilometer in diameter above the crater floor. That mesh would be shaped into a broad curve capable of reflecting very long radio waves toward a receiver held above its center. At the wavelengths involved, the reflector would not need to be a smooth metal surface like the dish of a satellite antenna. Openings in the wire could be many meters wide and still interact effectively with radio waves tens of meters long, dramatically reducing the amount of material that must be delivered. The natural crater would provide the surrounding geometry and support points, saving engineers from building a kilometer-wide rigid structure from the ground up. A proposed class of tethered robots called duaxles could help perform the deployment. A central vehicle would remain anchored, while a smaller two-wheeled unit descended the wall on a cable, carrying and fastening portions of the mesh in terrain too steep for an ordinary rover. Several robots working together could spread the reflector without requiring astronauts to climb into the crater. The completed instrument would be fixed rather than steerable, so it would observe a region of sky passing above the crater as the moon slowly rotated. That limitation could be accepted because the telescope's primary value would lie in sensitivity at wavelengths that have barely been explored, not in pointing rapidly from one target to another. The receiver, cables, and mesh would still need precise placement. A crater that is too shallow, too irregular, filled with unstable boulders, or poorly oriented would not work. Engineers would also have to prevent the supporting wires from sagging incorrectly as temperatures changed, and maintain the receiver's position over a structure larger than many cities. The concept remains an advanced study rather than an approved construction mission, and its final design could change substantially. Still, it demonstrates an unusual way of building on another world. Instead of flattening the terrain and forcing the moon to accept an Earth-like observatory, engineers could use an ancient impact scar as part of the machine, turning a structure created by destruction into an instrument designed to recover the faintest surviving information from cosmic history. Building an observatory. There would require surviving dust, radiation, and 2-week-long nights. The scientific silence of the far side comes wrapped inside one of the most unforgiving construction environments available to human engineering. A surface observatory outside the polar regions would experience daylight and darkness lasting roughly 2 Earth weeks each, forcing every component through prolonged heating followed by prolonged cooling. Near the lunar equator, exposed daytime surfaces can rise above 100 degrees Celsius before falling far below freezing at night, while equipment loses heat directly into space because there is almost no atmosphere to soften the transition. Electronics, cables, antenna supports, batteries, and mechanical joints expand and contract at different rates, creating repeated stress that can loosen connections or deform carefully aligned structures. The long night also removes sunlight from solar panels for hundreds of hours. An observatory would need extremely large energy storage, another dependable power source, or a planned low-power survival mode in which heaters protect essential systems until sunrise returns. Dust creates a different danger. Lunar grains are sharp because wind and water have never rounded them, and electrostatic charging can make fine particles cling to surfaces. Dust deposited on solar panels reduces power production. Dust on radiators interferes with cooling, and grains entering gears or connectors can cause abrasion and mechanical failure. Apollo experience showed that lunar dust scratched visors, wore through outer glove layers, contaminated seals, and caused equipment to overheat when it coated thermal control surfaces. A delicate radio observatory would also need protection from its own machinery. Motors, computers, power converters, communication transmitters, and robotic construction vehicles can generate radio interference far stronger than the cosmic signal being sought. So the machines that build and operate the telescope must be designed to become electromagnetically quiet during observations. Radiation adds slow cumulative damage. Solar energetic particles and galactic cosmic rays can disrupt electronics, corrupt stored data, degrade materials, and trigger unexpected changes inside computer chips. Shielding, redundant processors, error-correcting memory, and automatic recovery systems would be essential because maintenance crews might be absent, and Earth could not communicate with the site directly without a relay. Micrometeorites would add occasional physical impacts, while the vacuum could cause lubricants and materials to behave differently from the way they do in terrestrial laboratories. Even deployment would be hazardous. Crater walls can be steep, loose regolith offers uncertain traction, and one failed cable or robot could leave a giant instrument permanently incomplete. Building such an observatory is therefore not a matter of carrying ordinary antennas to a quiet location. Every part must endure darkness, heat, cold, dust, radiation, vacuum, delayed assistance, and the requirement to avoid polluting the very silence it was sent to use. The far side offers humanity an extraordinary window into the early universe, but the moon does not open that window gently. It asks whether our machines can remain precise in a place where almost every environmental condition works patiently to make precision disappear. Relay satellites must orbit beyond the moon to connect the hidden side with Earth. Beyond the moon lies a narrow region of space where a small spacecraft can become the only bridge between two worlds that cannot see one another. A relay serving the far side cannot simply circle close to the lunar surface like an ordinary mapping satellite, because during much of that orbit the moon itself would block either Earth or the ground mission. Instead, the spacecraft must follow a carefully chosen path where it can maintain long periods of visibility toward both. One of the most useful locations lies near the Earth-Moon L2 region, tens of thousands of kilometers beyond the moon's hidden hemisphere. A satellite cannot remain motionless at that point, because the gravitational balance is not perfectly stable, so it travels around the region in a broad three-dimensional loop known as a halo orbit. From this elevated path, Earth appears above one side of the lunar horizon, while far-side landers and rovers remain visible below. China's Queqiao relay demonstrated this method during the Chang'e 4 mission, receiving signals from the surface and forwarding them to antennas on Earth. The geometry, however, demands constant precision. The relay must know its position, point separate antennas toward two distant targets, manage limited electrical power, and correct its orbit before small gravitational disturbances gradually carry it away. Engineers also have to account for moments when the moon, Earth, or Sun creates unfavorable alignments, and for delays caused by storing data until the next reliable connection becomes available. Future networks may use several satellites rather than one, placing them in complementary orbits so that a rover traveling behind a mountain or into a deep crater does not suddenly lose its only path home. These spacecraft could provide navigation signals as well as communication, giving explorers a lunar equivalent of the positioning services used on Earth. They may also transmit data between surface bases, orbiting vehicles, and stations near the lunar poles before sending it across the greater distance to Earth. The relay, therefore, does more than repeat a message. It creates an artificial line of sight where nature provides none, extending human presence around the curve of another world. On the far side, the most important machine may not be the one touching the ground, collecting rocks, or looking into space. It may be the nearly invisible satellite beyond the moon, quietly holding open a pathway through which every command, discovery, warning, and human voice must pass. Future astronauts on the far side would depend on communication systems that cannot fail. On the lunar far side, a failed communication link would not be a minor inconvenience. It could turn an ordinary technical problem into an emergency no one on Earth could even see. Astronauts there would rely on communication for far more than conversation with mission control. Their systems would carry medical data, weather warnings about solar radiation, updates to navigation maps, instructions for repairing equipment, confirmation of spacecraft trajectories, and precise timing information needed to coordinate vehicles across the surface. If the connection disappeared while a crew was traveling far from its habitat, Earth might lose access to their location and physical condition at the same moment the astronauts lost access to external guidance. No real engineering system can be guaranteed never to fail, so the goal would be to prevent any single failure from isolating the crew. Several relay satellites could occupy different orbits, allowing one to take over when another loses power or moves out of view. Surface antennas could be placed on ridges and connected through local radio or fiber links, while rovers and habitats might communicate directly with one another even when Earth was unavailable. High-capacity optical links could transmit enormous scientific files, but lower-rate radio systems would remain essential because they are generally less sensitive to pointing errors, dust, and certain forms of interference. An emergency beacon might send only a few numbers and a short status code, yet those few bits could tell rescuers that the crew was alive, where they were, and what kind of help was required. The system would also need to survive long nights, radiation damage, temperature extremes, micrometeorite strikes, software errors, and the possibility that lunar terrain blocks a local antenna. Astronauts would therefore carry stored maps, repair procedures, medical instructions, and autonomous navigation tools rather than depending on continuous direction from Earth. Their vehicles might automatically return toward the nearest safe shelter after losing contact, while local computers would monitor life support equipment and make urgent decisions without waiting for human approval across space. Even during normal operation, the one-way delay between Earth and the Moon prevents truly instant conversation, so crews must already possess greater independence than workers at a remote station on Earth. The far side would push that independence further. Communication would remain essential, but survival could not depend on one uninterrupted voice from mission control. The safest network would be one designed to bend without breaking, degrading from video to audio, from audio to text, and from text to a simple beacon rather than disappearing completely. Future explorers would live beyond Earth's direct view, yet they could not afford to be beyond its reach. Their invisible lifeline would need layers, backups, and enough local intelligence to remain useful even when part of it had already failed. Why the Moon's hidden hemisphere may hold the final clue to how the Moon was born. The last missing chapter in the Moon's origin may be sealed inside a far-side rock that no mission has yet collected. The leading explanation for lunar birth begins with a colossal collision between the young Earth and another planetary body, followed by the formation of the Moon from hot debris orbiting our planet. That model explains many broad observations, but it does not answer every question. Scientists still want to know how thoroughly the impact material mixed with Earth, how quickly the Moon assembled, how long its global ocean of magma remained molten when its first crust became stable, and why its interior developed such strong regional differences. Near-side samples have provided extraordinary evidence, yet they come from a hemisphere altered by unusual chemistry, widespread volcanism, and several enormous impacts. The far-side highlands may preserve material formed under conditions closer to the Moon's earliest global state. A carefully chosen sample of ancient anorthosite could reveal the exact age and duration of primary crust formation. Isotopes within its minerals could show whether the material came from the same reservoir as near-side crust or separated while the Moon was still extremely young. Rocks excavated from deep basin walls might contain fragments of lower crust or mantle, offering evidence about how minerals sank and rose as the interior cooled. Traces of water and other volatile substances could reveal whether they survived the birth collision, arrived later, or remained unevenly distributed inside the Moon. The decisive evidence may not come from one spectacular stone. It may emerge only when samples are combined with seismic stations, heat flow probes, gravity maps, and measurements of the deep interior. Seismic waves crossing the Moon could reveal whether the far-side crust has a different internal structure rather than merely a different average thickness. Heat flow instruments could test whether the hidden mantle truly cooled along another path. Precisely dated basin material could establish which asymmetries existed before the largest impacts and which were created afterward. Each result would remove one possible history until only a smaller number remained consistent with all the evidence. This is why the far side may hold the final clue, Without necessarily holding a simple final answer, its importance lies in comparison. You cannot fully understand why one hemisphere became unusual until you study the hemisphere that did not share the same later transformation. For most of human history, we tried to explain the moon while seeing only one face and touching rocks from only that side. Now the hidden hemisphere offers a chance to test whether our story describes the whole world or only the portion that happened to face us. Somewhere within its pale highlands, buried basin deposits and deep exposed fragments may be the evidence that connects the moon's first molten hours to the divided world circling above you tonight. And perhaps that is the quiet lesson of the far side. What remained unseen was never secondary. It may have been preserving the beginning all along,